Hello, hello, hello. So this is our day 6 and we are starting out by creating something practical. So that's what it said to me that we'll be creating something practical. So today we'll not learn any theory. That's what it told me. And we have to, create something. So we are creating something using cargo. So today we'll not be creating just Rust files and compiling using our Rust C. We'll be using cargo. So phase one is that we'll set up a project. It will take approx 20 minutes. So we'll create the project using cargo and then we'll modify the cargo.toml file, which is profile.release, LTO, true, codegen, unit, up level 3. Now we'll do that. All right. So let's start by phase one. I have set up my, environment. Now I'll create cargo and new. All right. And what is it? Compute engine. So compute engine compute engine. Spelling mistakes. Don't make spelling mistakes. Compute compute engine. All right, same. Now, what is the flag lib? Something like library, but which library? What are we doing right now? So let's create. So creating library, compute engine package, and note is that see more cargo.toml key in the definition at dash dash dash. So let's ls we see our compute engine. Let's go inside compute engine. Ls, what do we see? Cargo.toml. It's tree, we see this much. All right, cat with cargo.toml. So we see it has name, version, edition, and these are only in packages, and there are dependencies. Do we have any dependencies? No. Then it says add profile release. So we have to, I guess, add this. So we can use, I guess, append. I've never used it, but let's try. And then we'll say, oh, we'll say profile.release, PROFILE dot RELEASE. No spelling mistakes. PROFILE RELEASE. Is it correct? Yes, release. Now we'll enter. We can't go back and erase because we are using cat. So yeah, LTO is equals to true. LTO is equals to true. Is it good? Seems so. Yes. Then we'll say code gen dash units is equals to 1. So code gen dash unit. Do we have to use s units? Yeah, units is equals to 1. So code gen dash units is equals to 1. Is it correct? I guess so. Let's move on. Now what is opt level, which is opt level, is equals to 3. Let's do that. Opt dash level is equals to 3. Is it correct? Opt level is equals to 3. Yes, it seems so. And now we press Control D. It's end of file. And now we say cargo cat.toml. And we see there is a profile.release and it has LTO true, code gen units, opt level 3. Yeah. So what it does is this ensures the meaningful performance measurement. We'll be, measuring some. We have been measuring, using Python. We have been doing those time, and we are doing that sort of stuff. So it is called benchmarking. So we also benchmark this, compute engine, which is made in Rust. So I don't know how we'll do this, but I know that we will do this. Now it says we have to go into source and create a compute.rs. So phase two is code trait architecture. Now this should take like about 45 to 60 minutes. So it says go to source, create a compute.rs, and then define a trait called compute. Inside that there is a method which is compute, which takes self, passes a and b, type i64, and result is, or return value is i64 again. And this is our trait. And then it says something like static exec then rs. So we have to create a few rs files. So let's go. Let's use vim. Let's create src and then compute.rs. We'll do like compute compute.rs. Seems nice. Yeah, seems same. Now we'll create what? We'll create, let it be. It is indexing now. We'll create public trait that is compute, and inside that we'll create a method which is compute small c. All right. So we'll create public trait just compute compute. All right. And inside that we'll create a fn method called compute with small c compute. It will take self, so ampersand self self, and it will take a which is of type I64, then it will take b which is again of type I64, I64. Then it says that it will give us result or return value which is again of type I64. All right, now this is the statement. So yes, I think we have created what it said is to be. Same, clear. Yeah. This file is not included anywhere in the module tree, so Trust Analyzer can't offer ID advice. We don't need it for now. So let's quit it. And then it says we have to create a static exec.rs. All right, we'll do that. It'll have a generic dispatch using static. All right. We'll go vim src static dispatch static exec, which is execute exec dot rs. So static exec dot rs. What we'll do is we'll use what? Use crate called compute. Inside that compute seems ulta. No, crate crate is compute. Inside that compute. It is a capital C. compute. This is also like this. So we'll use create, compute, and compute. Is this same? It looks same to me. At the end, we have to add semicolon. Now let's move on. What we'll do is create a public function called run static, which will have a type t, generate type t, or t, which is static. What is it? T generic value t, which is of type compute, and we'll have an engine which will be a reference to t, and then iteration which is u64, then it will give us a return value which is I64. So let's create that. We'll go like pub. Inside that we'll create a function called run static run static. No, before that we have t, which is of type compute small t, small c. Oh, big C. So we have a type compute. So like compute. Compute. Inside. After that we have engine. Uh, engine, which is of type ampersand t. And then we have what? Iteration, which is of u64. TERATION, which is of type u64. Then it returns as a value is type I64, isn't it? Yeah, same to me. Engine iteration. Iteration spelling is there. There's some error. Iteration, ITERATIONS. Iterations, sorry. Iterations. All right. Now let's go and define what it does. We'll now create a let mute ACC is equals to 0. Let mute ACC is equal to 0. This is a statement, so semicolon. Then for wildcard, which is underscore in 0 to iteration, we'll do ACC plus engine compute 2 comma 3. Why 2 comma 3? Why are we hard coding it? Compute 2 comma 3. All right, let's do it. So for this in IT iterations, one two iteration in the range of 1 to iteration. Is it good? 0 to iteration, sorry. 0 to iteration. Yeah, seems like it's correct. Then we have what we'll have is ACC plus equals iteration engine.compute 2 comma 3 engine dot compute then 2 comma 3. All right, semicolon because it's not a return value. Then we return this ACC. Everything seems correct and right. So this is a generic dispatch, but it's very short, so I think it will not work properly, but who knows. There is dynamic exec.rs, which is dynamic dispatch. Now we are creating another file, which is src. Let's go into src. All right, we go into what is there first? ls. All right, there is target. Let's make a tree. So in target, there is build steps, examples, incremental. All right, and in src we have everything. Let's go into src. Now we create static. Now we create dynamic exec exec.rs. Inside that we do the same thing. Use create compute. Use crate compute 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 big C, not small c. Big C compute and 2 colons. So yeah, create compute create crate compute create compute. Yes, we go add a semicolon. Now we'll create a function, a public function that is run dynamic. Pub function that is run dynamic, which will take a type of ampersand dynamic what compute compute. All right, hinge is of type dynamic compute. Run dynamic engine dynamic compute. Now iteration, which is u64. Iteration, which is u64. Then return value is i64 or u64. i64. Return value is i64. Then we define the method. We define it. Again the same thing. It's just we are running it dynamically, not statically. So same thing. Let what? Let ACC is equals to 0, isn't it? Let mutable ACC is equal to 0 because we are iterating over it. So mutable ACC is equals to 0. Then we are returning that ACC. Good for us. And over here we are saying for underscore, which is everything in 0 to 2 iteration. All right, 0 to iteration. What do we have to do? We have to do, is it like this? We have to create, yeah, iterations. We have to create this curly bracket. Inside that, we define that ACC is plus equal to engine dot compute uh, into that 2 comma 3. That's what we did. Engine compute 2 comma 3 semicolon. Seems all right to me. Yes. 0 to iteration ACC engine compute 2 comma 3 ACC. All right. After that, we have to create a file that is lib.rs, library.rs. We'll do that. I'm not here. Let's go save this. Not like this. So damn it. Escape. What is it? All right. So rest analyzer can't add. All right. Public function. I see some errors because this is red. So I don't know what happened, but everything seems right to me. Engine compute, ampersand compute, iteration. Iteration is of type U64. So yes, let's, word. Engine is of dynamic compute and iteration is of type U64. For that, everything seems correct. Uh-huh. You have double checked it. Yeah. Now there is no, whatever that error was. Now let's create lib.rs. So we'll create lib.rs. What is it? So we already have a lib. Why do we have a? Oh, let me just quit it for now. Let's see. ls. We created static. We created dynamic. We created compute. How did this lib.rs came automatically? How many files did we? We created compute, and we created this, and then we created this, and we have to create this public mod compute, which is lib.rs. We already have lib.rs. How, why, when? ls-la. Let's see. Lib.rs was at 702. So before anything, we started creating. Lib.rs got created. I think it is because of, cargo.toml that we did. So let's see what is inside this. So we have a function add, which is left, right, 264, left plus right. Inside that we have test, which is super and everything. Inside that test, it works. Then result is u64, left is 2, right is 2. Result equal, result is 4. I'll just delete everything from it. And we'll create our own lib.rs, which is public mod compute and then public mod static exec and dynamic exec. Let's do this first. Public mod compute, and then we'll do public mod, what is it? Static exec exec. Then we'll do public Oh, there is super. So public super. Mhm. I don't know how to take this. All right, let's not take it. Public mod and then dynamic, dynamic, exec, and then we'll create something like use compute, use then compute, and inside that bigger compute. But I think this is op like compute should come first with bigger C, because what we did, let me see, we created something like compute and inside that we have a compute. So it should be like compute first and then small compute later on. So why is it like this? I don't know. Is there a specific reason? I don't know. We have created what it said us to be. Then semicolon, use compute, and inside after that we have to create a public structure called adder. All right, public str. Can we use a mouse? No, we can't. Struct struct adder. So we have now adder. Inside that we have to implement impl. What do we have to implement? Or compute for adder. So we will say compute for adder, and what inside that we have a fn called compute. It might take self and all that, a b, self and a and b, yes. So it takes self, then a, which is of type I64, then it takes b, which is again of type I64. Then that's it. This we expect a return also. So uh, the result should be something like what should be, or it should be is like I64, I64. Yeah. Then inside this we will do a plus b, a plus b. Right. Now we have a phase 3 in which we'll create a benchmark binary, which will take something like src bin dispatch bench.rs. All right, we'll do this and we'll type all this. Okay, then we'll run. Oh, so this is the last step. Congrats, congrats. So we have to create bin, isn't it? Bin. And inside that, we have to create dispatch bench.rs. All right, we say bin, so dispatch dispatch uh, dispatch bench rs pmch.rs. Inside that, we will say use compute engine, use standard time instant. Inside compute engine, we'll say adder and dynamic exec and static exec. Good, good, good. We'll say use compute engine, engine. Inside that we'll say adder. Then we'll add what next? Static, static exec, exec, which will have run static, run static method. Isn't it a method? Then we have a dynamic, dynamic, dynamic exec. Inside that we have run dynamic. All right. Is there any problem? There is semicolon at the end. Let's see. Let's match. Use compute engine. All right. There is no space. There is two colons. Okay. Compute engine. Then there is adder. ADDER. Then static exec. Run static. Static exec. Run static. Then there is dynamic exec. Run dynamic. Dynamic exec. Run dynamic. Yeah. Seems so. And we'll use what? There's a standard time instant. So there's a library standard. Inside that we have a time. Inside that we have instant. All right, instant. Yeah, seems right to me. Then we are creating function main. Let iteration is equals to, oh my. We'll create 1 million instead of, no, let's do 10 million. And recording might stop, so because this will take a lot of load. But let's see how much fast is this Rust application. So let iteration is equals to 10 million. So function main, inside that we have non-mutable. Let it should be mutable, no? It's not, like right now it's not. So we'll say let ITERA iterations. Let iterations is equals to 10 million. Right? And we'll say let what next? Adder is equals to adder. So ADDER is equals to ADDER. Okay. Let adder is equals to adder. Iterations is equals to 10 million. And then we have static and dynamic. So we'll check for both. We'll benchmarking static and dynamic both. So we will say let's start and duration of static, then let's start, then duration of dynamic. Instant now and start elapsed. We'll say let start start, let's start. Then we'll have instant. Then we'll say now is a function sort of. Then we'll have semicolon. After that we'll have let duration, static duration, na? Or just duration? Duration static, duration dynamic. Duration. Here it is STATIC, which is time elapsed. Start elapsed already. START dot ELAPSED, start elapsed. We'll yank J and we'll paste it. We have something in, oh sorry, DD, oh, that we say let what? Let result static is equals to run static, and then add an iteration, right? Let result static is equals to run static. Inside that we are sending it ampersand ADDER, and we are sending it ITERATIONS, patience, right? So we have a result static which has a run static function or method. Inside that we are passing adder and iteration. So let's see. Result static, run static, adder, iterations. Result static, run static, adder, iterations. Seems nice to me. Then we'll have a result dynamic, run dynamic, adder, iteration. Okay. We have a let result result dynamic is equal to run dynamic, and then adder, capital and small a, and then iterations. All right, iterations, everything. We don't have a comment, so we'll add a comment like this is dynamic. Dynamic what? Nothing, just dynamic. We have this as a static, static what? Nothing. So we have dynamic, we have static. Okay. After that, what do we have? We are printing then static result and static time, which is result static and duration static. Then we are printing result dynamic, duration dynamic. Okay. So we'll say print ln, print ln, print ln. It looks like this. We have this inside that, this. Then we are passing result, result static, result static, and then we are passing, blanket, and paste it, paste it again, paste it again. So now we have result static, we have back CB, we have duration, duration static, and then we have result CW, result dynamic, then we have result duration dynamic. So let's write it down. Duration dynamic seems nice to me. There's one more mistake. We have not renamed this. Duration dynamic. So we have start, which uses instant and then now. Then we have result static, which sends run static, adder iteration. Then we have duration static, which is start dot elapsed. For dynamic, we have instant now, which is start, and then we have result dynamic, which is run dynamic, which is adder and iteration, and then we have duration dynamic, which then has a start dot elapsed. Okay. We have print statements which print result static and duration static, and then we print result dynamic and duration of dynamic. So what next? Dynamic result, dynamic time. All right, so for dynamic time or for using time, we are using debug. We are not debug printing. So we'll say this is static result and static time, something like that. We'll say okay. static static or ESULT static result, and then over here we'll say static static durati, duration. Okay, so we have static result and static time. 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 Static res For this, we have to use debug. It looks nice. We have then dynamic result, the dynamic result, which is this. And then we have static as no dynamic time, dynamic duration, dynamic duration, which is again for time. We have to use debug printing. I think we have created it. Every comma, every semicolon, everything looks the same to me. Now we'll just exit it and we'll say cargo run release bin dispatch bench. From where? From anywhere or just we have to go? You know, W2, we say CD, one more CD. Yeah, now CD come to engine. From here, I'll say cargo run. First of all, clear everything. You say cargo. Let's see what happens. Cargo run and then what? Release bin dispatch bench. We are using release re release, and we are using another flag which is bin. And then we are saying this. We can get a flag, but we can't get dispatch bin. What is it? Dispatch bench. DISPATCH. Inside that BENCH. I think that's the name which is the program inside binary. So dispatch bench. Dispatch bench. Yeah, looks right to me. Switch. Dispatch bench. There's an error. What is it? Help a local variable with a similar name exists. Iteration. Ho ho. Ho 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 ho. So in dynamic exec, we have to go. Let's go into SRC. Dynamic exec. Line number 5. Line number 5 is this. So we have used iterations over here and we have used iteration over here. So we'll just say add iterations. It looks good to me. How about now? Shit. Okay, so elapsed is sort of a method or function we have to use. Where is it? Yeah, this. So let's go to dispatch bench, which is inside bin dispatch bench, and for all the elapsed we have to use double brackets. Now let's go to elapsed. No, ELA. Yes, go there. End the word, append it with this, then go to the next one, end the word, append it with this. I think we are good to go again. I think so. Let's see. Building, dispatch bench bin. It's taking time. Oh my. I've never spent this much of we have a static result, which is it was running. Oh damn. It was running 10 million and it took about 129 nanoseconds and the dynamic took about 59 nanoseconds. So here the static duration is more than dynamic. How the hell would that happen? Like dynamic duration should take more time. That's what we expected because the static duration, the static method or the static trait or whatever that's static dispatch, what is it? It gets converted into binary. So binary should always be faster, no? Than whatever this is. So let's just copy this result first of all. We are happy that it compiled and we didn't need to ask any help. And let's paste it. We are not sending it right now. We are building. So Now record the static time and dynamic time. We have it, but I don't think it's good enough. And then check the binary size of target release dispatch bench. All right, ls lh target release build target release dispatch bench. So it is size of 380K, right? This is the size. It's copied. Let's paste it over here. Hmm. Now phase 4, which is error modeling, which is 45 to 60 minutes. So we are now creating error.ts, all right, which looks something like this. So let's go derive debug, pub enum compute error overflow invalid out input. So we are creating an enum, which is called compute error, and inside the compute error, how many sort of errors that can happen is overflow and invalid input. And we are using derive debug so that we can use predict into it. Let's see, is it overflow or invalid input? Ah, so we created it almost, but this is invalid input. Looks like this. Invalid input. Now, does it look good? Public enum compute error, overflow, comma, invalid input, comma. So we'll add comma. That's it. We'll quit it. And I think we have to modify the trait compute. So where was the trait compute? Oh. So let's see inside each file. Let's go into src dispatch first of all. Do we see any compute? Run dynamic. This is run dynamic, but we need something like function compute. But it's not over here. So I am guessing it will not be even inside, uh, uh, so dynamic exec doesn't has this. So I think static exec also doesn't has this. Errors.rs, that is we have made this. So we'll go either in lib.rs or compute.rs. So I think I'll go to compute.rs. Yeah. So here it is. So we have to, change the result or the return type. It's like, damn it. Ah, just go over the words. Hmm. So we'll say result is inside result we have I64 and computer. Oh, RESULT triangular brackets, comma, and COMPUTEERROR. All right, I think so. Looks correct to me. Mhm. compute error. I'll just let's see what is inside lib.rs. Can we understand it now? Lib.rs compute dynamic exec compute. Over here too. We have to change this. Thank God that we went for this file also. Otherwise, it would have created some ruckus. Result. Now we are expecting the return type as result, which has first of all I64, and another thing it has is enum that we declared, which is compute, compute error, compute error. That's it. Modify the trait compute error everywhere. I have. Let's exit it. I think this is not it. I think we don't have to do this over here because, yeah. First of all, this is, I guess, not a trait. This is implementation for adder. And this is, looks something like this, but this is not a trait. Yes, this is not a trait. This is not a trait. What was the trait? This was the trait because, we see a semicolon over here. We see a semicolon over here. Not inside that, not outside that. Now let us also see what is inside bin and dispatch bench.rs. It has nothing to do with all that. So now what? After doing this, update the implementation. That's what I was trying to do. The implementation was going to change, but we also did this. So A checked address B, A checked add B, and then OK or compute error overflow. Okay, so we have to change the whole implementation. So now we know where the implementation lives. We'll just go there, src. Where does it live? It lives in lib.rs, isn't it? Yeah, we see the implementation over here. So we'll go to 9j. And we'll make it, not append it, make it SULT, and then I64, and then compute error, COMPUTE, compute error, and that's it. Now we have to change this, so remove it. Now we have to say add a.checked add. Now we have to create checked add now. Or it exists. Does it exist on Rust automatically or it exists? So we have to create checked checked add. Inside that we have to send. So checked error takes self and then RHS value, which is I64, and then returns option, which is I64. So checked integer addition, which is compute self plus RHS, returning none if overflow occurred. Okay, so we are using to prevent overflow, or if it occurs, we must get to know that overflow occurred. Then if okay, then it's all right, or we say compute error, which is overflow. We go like okay, not clear, okay, or we go like compute error, COMPUTERROR, and we say overflow. Exactly this, or do we need some change? Compute error and then overflow, compute error, overflow. Good. Now I think we should exit it and we might not see any errors. Modify the static or dynamic execution to propagate with question mark. Okay. It says that modify dynamic and src static rs to compute with sort of question mark. Is it good? Is it bad? I don't know, static and dynamic execution to propagate with question mark. That's how we do it. But is it good? I think so. Yeah, looks good. Looks good to this. As for dynamic, go like it could- I think we have done what we needed to and compile cleanly. So we have to compile again. Let's do it. How do we compile again? We say cargo run, release bin, dispatch bench. Oh my. We have compute error, compute for adder. What it says is, okay, not found in this scope. So we have to implement compute error, compute for adder. Then it says the same thing over here. So let's go. Let's go. Start with compute.rs, then we'll have to go to lib.rs, and then that's it. That's it. So let's go to first of all compute.rs. So we go like pim src compute.rs. Inside that, does it look good first of all? It does look good. But what we have to say is, what do we have to say? Inside this, we have to, public create compute and then pass compute error. In compute, we have to pass compute error. In compute, we have to pass compute error. And PUTE But we didn't see any sort of error, so we just passed. As for lib.rs, we have to go back and say implement compute error. So we'll say vim src lib.rs, and then we have to implement. Inside implement, we have to say compute error for compute error, compute for error. Compute error, compute for error. Compute. COMPUTE. Compute error. And then compute for error. That's what it said. Now there is use of undeclared type compute. I guess it should work. Let's see. Shit. Associated item not found in. Okay. So now what we have? Oh my. Shit. Shit. What do we do? What do we do? In dynamic exec.rs, it expected one generic argument. Compute is not. But it works just fine now. Now it says in compute.rs, missing generic argument. Like T or something like that. What is it expecting me? Missing generic for trade compute. Trade defined here with one generic parameter, that is compute error. Now public trade is this, add missing generic argument. Compute and compute error. That's what it says over here. Iteration is missing generic trade for compute. It's happening. And same for static one, I guess. You know, compute error. Public trade compute. It says compute and then inside implement Oh, I'm sweating so hard right now. My God, what is this? I don't understand. What are we trying to achieve? What are we doing with this? I know we are benchmarking, but still, what is this? Let's go with new wing now. Let me make some adjustments like shift it to workspace 3, workspace 2, make something like this. Let's go to project learn last day 6 or 06 day. Over here, cd into whatever you find. And we are here. We'll say build build. Not like this. We'll say cargo build, not build. And cargo build says something like pin, but before pin it was something like something more. What is it? Profile, package, target. Something like target. Let's see. What was it? Release and then dispatch bench. Cargo build nahi cargo run. Cargo run. Run. Then release. Then we go like dispatch. DSPATCH dispatch. Dispatch what? Dispatch bench. BENCH. And we see many errors. We'll sort it out one by one. So now we go to dynamic exec. Let's go to dynamic exec. And over here, what do we have to do? It says public fn run dynamic and expected one generic argument. So over here, it expected one generic argument, which is compute error. Let's make that possible. For we say we have to insert what? You have to insert COMPUTEERROR. It doesn't seem to even recognize it. So, all right. Does it look nice? I think so. It says so. Let's do it. Now there is line 1 which says compute over here. Nah, it looks different. So it is compute.rs. So I think this dynamic exec is complete. Okay, so let's save it. Then we go back to uh, compute.rs, and what it expects me to say is it says compute and compute error. Is it wrong? Missing generic argument. Damn it. What can I do to make it right? Okay. Missing generic for compute. It is now static exec. Let's go to 3 and 20. Static exec. Let's go to line number 3 and then 22 character. Just right here. We'll add compute error to it. That's it. You have to insert what? Compute error. Error to it. And I think that's it. Inside lib.rs, what is it? Expected one. My God. So we have to add this now to lib.rs. Compute error exists over here, but we have to add this for here. What the hell is going on here? So let's go to lib.rs and let's make that change. Let's make it happen. Let's go to lib.rs and let's make that change happen. Somewhere over here, it expects us to, be add something like compute error, compute error. Is it good? Is it bad? It is what? I don't know. Associated item overflow not found for this parameter. Did we do some spelling mistakes? Let's see it. Oh, sorry. We gotta use visual. Okay. This is this. Lib.rs is this. I don't see any errors. This is this. This is overflow. It has overflows. Why can't it find it? Compute error. We have enum called compute error. Doesn't find overflow. Spelling is same. Overflow. Let's check one more thing. Overflow. It says exactly like this, so there's no change to it. Okay, or compute error is now double colon at overflow. That's what it says. Okay, underscore, then or then parent. What is this? Bracket, compute error, overflow. So what is the issue? Okay. Now save this. Save changes. Yes. Clear. I think we'll run this. Ah, shit. The errors are increasing. Shit. Or it's telling me to add compute error over here, but we have error over here. So it's trying to, oh, so error is this much only. It's not this. Okay, okay. So let's not see it over here. Let's make everything clear. Then let's run it. And we see there is only, not only, but still there exists an error in dynamic exec over here. It says add this, and in static exec, what it says is, I don't know what it says. Not found in this scope. So what do I have to do? First of all, make this change. Then we'll see if this error persists or do we get a new error. So dynamic exec.rs. We'll create new them. Dynamic source dynamic exec rs says this starting. JK. No, no, no. We have to over here. I guess I have to insert it or expects compute error somewhere here. See line 3 expects compute error. Let's make it COMPUTE and error. I think let's save this. Let's go around, run. Error has not decreased, but it now says the static one is now there. It persists. But now we have like option to accept. Cannot use this operator in a function that returns I64. Where should we return? Where should we use it? Now it has new error, which is like associated overflow is not found. Why not? Compute spelling is same, overflow spelling is same. Let's now use pdump. Pdump of this location. And let's go to 3. And something has gone wrong after making changes for this for phase 4, isn't it? For phase 4. Here is the code. Here is the code. Let's go. Good. Two separate issues here. Issue 1, the benchmark is completely wrong. Yes, it is completely wrong. 10 million operation in nanoseconds. Impossible. Optimizer removed your loop. Why? Because adder.compute 1, 2, 3 is pure. Inputs are constant and result is deterministic. Compiler inlined everything. It replaced the entire loop with something like this. So 5 times 10 million. Now the benchmarked constant folding. Fixed mandatories inside both loop prevent optimization. Option A is simplest, that use hint black box and use it in black box. So it knows it exists, but it doesn't know what exists. So also black box ACC after the loop. After the loop, we have to add this black box ACC. This prevents LLVM from removing work. Rerun the benchmark if time are still nanoseconds, still wrong. Expect milliseconds. Issue 2. Your error architecture is conceptually broken. Your error architecture is conceptually broken. Why? You turn compute error into a generic type parameter. How? This is incorrect. Public trade compute error. You already defined compute error. You do not make it generic unless you want pluggable error types. You created a generic type parameter named compute error that shadows your enum compute error, causing impossible implementation like compute error for adder. This means adder works at any error type. That makes no sense. I also think so. Doesn't make any sense. Now there is a compute correct architecture is compute RS. Beside that we have create error, compute error. All right, and then we'll use it like this. So let's go to compute RS and let's make the change. CW, remove this, remove this, remove this, remove this. Okay, Explorer, compute.rs. Let's go. Mhm. What we have to do is remove this compute.error and instead what it uh, says is use then crate create error and then inside that it says compute error. That's what it said, no? Where is it? Yeah, over here. It says in compute.rs use create error compute error, then make it something like this. Semicolon and use create error compute error. It says use create error compute error. Then public trade compute. Yes. Inside that compute self takes AB. Result is I64 compute. Shall we move on? So no generics. Okay. In static exec.rs, let's go to static exec.rs. And what shall we do now? So instead of making all these funny things, we should have just, you know, use crate create compute nahi error, then compute error error, then compute error, compute error. I think that's what it says. Compute and then compute error, which is compute error. And then it says a function this run static, function this run static. Say that engine ampersand t, engine ampersand t. Iteration is u64, iteration u64. It returns a result. It should return a result. It should return a result. So at the end, here, return a result I64, comma compute EROR, compute error. Mhm. Now it expects I64 and compute error. Then let everything is correct except now this I as I64 comma 3. Over here, come up, down, C to double I as I64 comma 3. Then we have to send OK, ACC. Compute error, T iteration result, compute error, oh, 0 iterations, ACC is equals to engine.compute, I as I64. Now dynamic exec.rs. Let's go. Dynamic. No, 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 no. Shit. Dynamic exec.rs. Now what we have to do over here, first of all, remove this funnily looking thing. This must go. C U W. And over here we have to say result, RESULT, which is then I64, and then we have to use compute error. We have to say use create, that is now error, and compute error, COMPUTEERROR, compute error. Okay. Is there any other changes? Replace with I, and it says for I in the range 0 to iteration, we do now engine not compute. Instead of 2 comma 3, we now use I as I64 and 3 J C1 W I as I64 comma J. Then what we have to do is return OK, that is OK, capital O, no? OK. It's a big OK. Okay, everything seems as it should be. Let's move on. lib.rs, something like this. Result good, compute overflow good. I think this is where we made things funny. Right, quit. Save all. So say A. There we go. And then src inside that lib.rs. Come over here. Delete for delete forwards. Compute for adder, and then it says fn compute self a v, and then result is I64 compute error good. Then a checked add B, or compute error, which is overflow. All right, we have to just you know, use crate, which is error, and which is computerror. Future, what is it? Uh-huh. What the hell? Why no crate? Why is it without any crate? So let's do what it says. Let's do what it says. But we used crate now over here. Yeah, there are no crates. Beautiful header and whatnot. I think it's done. 1, 2, 3, 4. Oh, we have to add public mod error. Again, we would have done something stupid. Public mod error. Public mod error. Now we have to go in nvim src and bin. We have to change this dispatch bench.rs. Dispatch bench.rs. Say that first of all, compute engine, which is add a static exec, dynamic exec. Compute engine, add a dynamic exec, static exec. Looks the same except for comma over here, but doesn't matter. Then standard time, which is instant. Then we'll use standard hint and black box, std, and then hint black box, and then black box black box, standard hint black box. In the main, we have iteration, we have adder, same, and we have static, result, and duration. But right now we are not printing the results. Why not? Nobody knows. GCC. We are only curious about the duration. And as soon as we get the duration, we'll check if we can print it. In main, everything seems correct except for the result static and result dynamic. We have to run. We have to run dynamic, unwrap. It said don't use unwrap, but let's use now. Then black box the result static. Then and says use dot un rap unwrap, and then it says black box the result static. black box the result dynamic. Same, no difference. We yank it, we paste it, we change it, static. At the end, we append the unwrap. Okay, we are printing the durations only. Durations. All right. Now, what You did wrong conceptually. Misused the generic for error types and shadowed in a name. Benchmarked, optimized away the loop, and measured nothing meaningful. Now this is good. You hit real world pitfalls. Now I test you. First of all, let's first run it. If it does, run. Oh, oh, I not found in the scope. Yeah, I thought so. I thought so that I made some mistake. Because how would it just go so smoothly? Static. Okay, SRC, then static. Inside, I see, I see. Let's replace it with I. Now we have I. Let's go. Let's run it. Trans. Let's see the numbers. 10 million. This is nanosecond, 83 nanoseconds, and now dynamic is more faster. It microsecond is more faster, no, than nanosecond. Nano, micro, pico, something like that. What the hell is this? I get compiled and go out quite fast, I guess. Now let's try answering these questions. Why did LLVM eliminate your loop? Because Rust is unsafe. No. Why did? Because optimization, something like that. Because trade objects are optimized. The instant is inaccurate because computation was pure and constant. Question 1. Answer is C. Since it was pure and constant, it optimized the loop, which resulted in some wrong readings. What is wrong with trade, compute, and then E? In your case, nothing. Forces dynamic dispatch, introduces unnecessary type parameters, it makes trade object impossible. Trade and then compute E. It introduces unnecessary type parameters. It forces dynamic dispatch. I don't know. It makes trade object impossible. Let's go with the C. Now, why is black box unnecessary in benchmarking? Explain in one sentence. I think BLACK box is being used so that the loop doesn't get optimized by the compiler. COMPILER. Let's go. Good. Your answer is correct, conceptually correct, but incomplete. We know that. Now we analyze what just happened. Your benchmark is still wrong. 83 nanoseconds for 10 million iterations, still impossible. That means static path was optimized away. Dynamic path was not fully optimized. Why? Because generic static dispatch was fully inline, constant propagated again, and dynamic dispatch prevented the full optimization. You are accidentally benchmarking the full eliminated loop versus the real loop. So which is bigger? Nanosecond is bigger than, let's search. Nanosecond and microsecond. Which is BIGG? Yeah. Micro SECOND or nano SECOND. Nanosecond is smaller, microsecond is bigger. Nano is 10 to the power minus 9, micro is 10 to the power minus 6. So microsecond is 10 to the power minus 6. Good. So it is bigger. Nanosecond is smaller. That means 1 microsecond is 10,000 times longer than 1 nanosecond. Oh, oh, oh. So what happened here is static duration Well, it looks like it ran quite too fast, or it shows that there was some, optimization. It's looking like fully eliminated loop. So it sort of eliminated the whole damn loop. And dynamic was benchmarking the real. So that is not fair comparison. I know. What can we do? Why static got eliminated? Now, deeper reason is in static case, the run static is generic, ADA is known at compile time, and compute is small and pure. No, but we did not. I as I33 plus 3. It's still predictable. Oh my god. So LLVM may vectorize or pre-compute some formula, and compiler sees this sum. It replaces loop with arithmetic formula. And dynamic cases, the trait object prevents the inlining. Compiler cannot reason about the implementation, and loop remains. So you measured something like algebraic simplification versus virtual call loop. So there was a virtual call loop in dynamic case and algebraic simplification in static one. So the correct benchmark fix would be you must prevent inlining and prevent constant folding, prevent loop algebra simplification. How? So in lib.rs, we'll add something like inline never over here. Okay, okay. So we go to neogame and src. Let's get into src. Okay. cd src. Then we go ngame lib. We say inline over here. What do we say? Inline never. We say hash, and inside this we say inline. Damn it. Append. We say inline. Shit. We don't use it like this. We just have to say inline and then in bracket. We say never. Capital N, small n. Never, small n. Never. Oh, oh. In step 2, add black box on input. So over here we are adding black box in both static and dynamic. Okay, okay. Step 3 is black box final result. In benchmark binary, use black box. Yeah, we did use it, but let's do this first one. Step 2 is we have to say this, X is black box. Let's just copy it. Static and dynamic. So let's save it first. Then we'll go to static. Then we'll go to dynamic. So before going to that, you have to just, oh, not like this. You have to say, oh, oh. You have to say, oh, he, oh, and paste it. And over here, instead of using I, we use X now. So X and 3. So now this is our static exec. So we save it, we don't quit it because we now need to go to dynamic exec. We'll do the same thing. We'll just open up a new line, we'll paste it, come up over here, we say use X, I think we are good to go. To all. Now step 3 is black box final result. So in benchmark binary, we do this. We have this, I guess. Not guess, but I know it is there. Pin and then benchmark. We have this black box result static, black box result dynamic. Now rerun. Both loop must execute. Static should be slightly faster. Expect milliseconds. Expect 5 to 20% delta, not thousands and more than that. Mhm. Black box not found in the scope. Why? I didn't use this. Okay, so let's just copy it and we'll paste it. Static, come up over here, just print it. Use new line, not as this. Just save it. Where is the dynamic one? Come up at top, print. Oh shit. Use, not like this. We have to say use what? Create print BLACK box. This is what we create hint black box. Looks good to me. Aha. Standard hint black box. Standard, not create. So standard and hint and then black box. So change this to standard and then hint and then black box. What is W2A? Now we try to run it. It runs. Now I think it's running because static is now taking more time than dynamic. This might be wrong too because it shouldn't improve your question 3. Correct answer is black box prevents the optimizer from making assumptions about value and ensures that the code under benchmark is actually executed. So version lacked the optimizer assumption explanation. That's why precision matters. New concept question is, don't ask me question right now, but let's answer it because it is only one. Why did dynamic dispatch prevent algebraic simplification? Because implementation is not known at compile time. Simple. Very, very simple. Yes, fourth is C because our implementation, fourth is B because implementation is not known at compile. Good. 4B, correct. The concrete implementation is not known at compile time, so LLVM cannot perform devirtualization or algebraic simplification. Now we analyze your benchmark. The dynamic is slight faster. Why? Nobody knows. That means you're not measuring the dynamic cost. Oh my God. You're measuring something else. Let's reason carefully. What is happening? Each iteration does checked, add, and overflow check, then result construction, then question mark branching, and then accumulation. The cost of dynamic dispatch, which is one indirection plus v table lookup, is tiny compared to the branch prediction, overflow check, and loop mechanics and black box barrier. Now the dispatch overhead is drowned in noise, so delta is 0%. Now this is realistic. You learned something important. The dynamic dispatch overhead is often negligible when real work exists. So you actually measure something called dispatch cost. You must isolate the dispatch overhead and make compute trivial and branch free. So change compute to something like inline never, and what is this? Okay compute, and is that it? Change compute to something like this. Remove checked add. Okay, we will. And vim and compute. We'll remove. Ah, there is nothing in compute. So I think this is not the place it wants us to change compute to. I think it wants us to something over here, or oh, not here. Not compute, then errors, not errors, then what? Lib. Yeah, over here we should now just send OK. So we'll just delete this. We'll open up a line. We'll say capital OK. We'll just A plus B, as simple as it could be. Everything looks expected. Inline never. Yeah, looks fine to me. W. Then we'll say quit all. Remove. Now keep the black box. Now rerun. Our dispatch cost should surface. Expected is slightly faster, like 15 to 5 to 15%. Let's run and test it out. Static duration is still sort of taking more time than dynamic duration. Why is that? Now it is taking more time. How about I try to run it again? Now it's the same time. Again, now static duration is less, now dynamic duration is more. Again, now static duration is out of bound like 41 and dynamic duration is 21. So what is the issue now? Important insight was that your previous 89 nanoseconds and 49 microseconds result showed that static was optimized into a formula and dynamic prevented full optimization. Now you're seeing that when real work exists, dispatch difference vanishes, and that is exactly why dynamic dispatch is often acceptable in real systems. Whereas in concepts, static is always faster. Now, concept check. Okay, I have some concept checks, so let's do it. So one, if dynamic dispatch overhead is more than 5 nanoseconds per call, overhead is what happened to the relative overhead when each call does 200 nanoseconds of real work. It increases or it becomes negligible. Question one. So 5 nanoseconds per call, and if it does And when each call does 200 nanoseconds of real work, well, it becomes negligible. I think so. Why can static dispatch sometimes produce larger binaries? Why can that be? Might not fully a few optimized by a compiler. Why static dispatch can sometimes produce large binary? Not this. Large binaries are because of because it might duplicate the tray for EVERYELEMENTS, like the add and multiply both. Hey, let's not give it example right now. It might duplicate the trait for it might duplicate the trait for every element instead of just having one, which cannot happen. So let's not write it. It can only happen in dynamic. So yeah, in real world system, where is dynamic dispatch typically acceptable? Hot inner loops. Mhm. Performance critical math. Nah. Plugin boundaries, abstraction layer. Yes. SIMD code. No. 3 is C. Modify compute to remove checked add and rerun the benchmark report static time timing type ratio. We are not calculating ratio right now, and ratio is not calculated. We are isolating dispatch cost scientifically. Well, you are correct, but imprecise. Precise version would be static dispatch causes monomorphization, generating a specialized copy of generic. Yeah, causes monomorphization, generating a specialized copy of the generic code per concrete type, not trait, per concrete type. Now that increases the binary size. Another important part, static is 30, dynamic is 22. Now dynamic being 25 times faster than static is not realistic, but that's what we are seeing. Dynamic dispatch cannot be inherently faster than static dispatch in tight loop when doing identical work. What is happening? Root causes. Static version is likely being inlined, then combined with black box, causing register pressure to preventing optimization, or compiled differently due to generic specialization. Meanwhile, the dynamic version not inline, cleaner loop, possibly better code layout. This means you are now benchmarking code gen artifact and not dispatch cost. We must inspect the real difference. Now answer this carefully. Are both functions structured identically except for tcompute versus ampersand? If not, your benchmark is invalid. So let's use p dump again. Over here, copy everything, go over here, paste everything, and you see it for yourself. Good. Code inspection first. You did not remove the result. Your trait is still this, and both execution paths still use. So you're not isolating dispatch cost. You're measuring result construction, branching from error type handling and addition and loop black box dispatch. Our dispatch is only tiny fraction, so we must isolate it further. Hmm. Which we. Hmm. Proper isolation version is like final form. Change everything to this minimal structure. A compute RS will be public trade compute and function compute. Self will take A and B, will return I64 value. So no result, no error enum, and no branching. Proper isolation version, like final form. So change everything to this minimal structure. So compute RS will become this. Let's go to compute RS then. Here is compute RS. Compute RS becomes the minimal version. Like that was the earlier case, wasn't it? Uh, CD, remove this, remove everything like that, and we shouldn't even need this. So let's our GCC it. No result, no nothing, everything looks good. librs becomes this. So we go like and we have lib.rs. It becomes just this, so minimal version. Public struct adder is there and nothing else. In implement compute for adder, then inline never, then compute cell, no result should be there. So remove this, okay. Uh, and remove this result, just return I64. Okay, now static exec rs becomes this. Let's take this first of all. Shit, what did I do? Undo. No. Static exec becomes something like takes compute, engine compute, gives result that is I64. So 100%. Now this gives result that is I64. Okay. Let mute ACC is equals to 0. and everything looks correct. Okay. Like, okay, should be removed. And yes, dynamic exec.rs. So just save it. Now let's dynamic exec.rs. What we'll do is remove the result from here also. Go to CW, remove this, become like CW, remove this, and we'll remove then the okay. Now it becomes this. Okay. We don't use any question mark, so let's remove that X. Did the static exec had the question mark? Let's see. And the question mark. Static exec. Yeah, it did have a question mark, so let's remove that too. Go back, remove this question mark. Isn't it? Yeah. We removed everything. Now what? Dispatch bench.rs, remove unwrap since no result. First of all, let's remove this explorer. Let's save it all. Now let's go to buffer. Dispatch. Where is dispatch? Dispatch bench.rs. We have to remove unwrap. We have to remove this. See, send this thing. Um, then cargo clean, cargo run. All right, let's do that. We'll say cargo clean and cargo run release bin bin what? Dispatch. Yes, EATCH then BENCH. Dispatch bench, isn't it? Yeah. Oh shit. It's just a warning. Yeah. Now we have a static duration that's taking more time, whereas dynamic duration is taking less time. How is that possible? And why is that even there? Let's go. Now you have isolating loop, nothing else. Why this matters? Dispatch overhead. But even if you are telling me all these concepts, but doesn't make much sense to me because we are not seeing practical results. Your numbers are this, so dynamically is significantly faster. Why? Theoretically, it's not. Whereas over here, it's like half times faster, more than half, but still. Dynamically is significantly faster. This means one of the two things, like static path is being optimized differently, like worse code gen, or your benchmark is still isn't symmetric at machine code level. Reason careful. What actually happens is static version is this. This is generic with LTO enabled. CodeGen Unit 1, the compiler can specialize inline aggressively and restructure loop, possibly interfere with black box. Dynamic version looks like this, and this is monomorphic at call side, so it may generate a simpler loop with predictable structure. So your result likely reflects code layout plus inlining plus LTO effects, not raw dispatch. Critical insight. So critical insight. So the dynamic dispatch cost is roughly one pointer dereference, one indirect jump, so 3 to 8 CPU cycles. Loop body does loop increment, black body barrier, addition, accumulation. So dispatch cost is small compared to loop mechanics. If static is slower, it means inlining interfaced badly with black box, register pressure increased, code size grew and hurt the L cache. Let's go and reduce the code size. So let's go to lib cargo clean and let's go to nvim lib.rs. Let's clean. Oh, what was needed to clean? We need to clean the line 7. Here's the line 7. Line 7. Let's clean this. Let's clean this also. I don't think so. How about this? No. So in static exec, we should clean static exec line number 2. So let's go to line number 2. Let's clean it. In dynamic dispatch, we should clean the line number 2 again, which is compute error. Any other warnings? No, only 3 warnings. So let's now run new. So static duration is still faster and dynamic duration is still slower. Sorry, static is slower, dynamic is faster. What should I do then? Just speed up everything again. Before speed up, let's copy this. No need to think right now. Just at least achieve what we need to benchmark properly. Now we think like an engineer and answer precisely. One precise. Why can large inline code sometimes run slower than smaller indirect call code? Because of optimization. Everything is on optimization. Why does the code gen unit 1 2 in release mode enables dynamic dispatch? No. Disables the LTO? I guess so. Forces single compilation unit for better cross-function optimization. Yeah. So the two is B, and 3 is if we disable LTO, what do you predict will happen? Static becomes slower, static becomes faster, no change, dynamic disappears. Static becomes slower. 3A. Question 3 first. So question 3, if we disable LTO, what happens? Correct answer would be, correct reasoning would be, LTO allows cross-module inlining and whole program optimization. So disabling LTO reduces the optimization opportunity. That's why I said that it will become slower. That's what I said, no? Uh, Static becomes slower. That's what I said. So it says now, so static dispatch loses some aggressive specialization power. Therefore, static should become slower relative to dynamic. You wrote 3A, which matches A, so conceptually correct. Alright, what the hell? Just analyze my numbers now. Dynamics still faster. Now we reason deeper. Critical observation is look carefully. All right, I'm looking carefully. There is a function which is public, non-static, compute, engine, iteration, 264. This is now dynamic compute, iteration, U64. Static version is generic, dynamic version is monomorphic. But this matters. Even though static dispatch avoids V-table lookup. So static version is generic and dynamic version is monomorphic. Static version is generic and dynamic version is monomorphic. This matters. Why? Even though static dispatch avoids V-table lookup, the function itself is generic. This is generic, no? This is dynamic. Dynamic became monomorphic instead of polymorphic, and static became sort of generic. But well, it was, but this matters. Even though static dispatch avoids V-table lookup, function itself is still generic. So generic function sometimes produces slightly worse loop layout because the function body is monomorphized, and but the code may be duplicated and inlining decisions differs and register allocations differs. So dynamic version, which is single concrete function body, which becomes a single concrete function body, whereas simple lookups and one indirect call potentially better I cache locality. And then in tight loops, the instruction layout matters more than a single indirect call. So what you're observing is the code layout plus register allocation is greater than dispatch overhead. Now this is real compiler level effect. Final isolation. We go one level deeper. Now change the static version from generic to monomorphic. So we'll remove this and we'll go something like with use create adder. Then we'll go like adder. Okay, no generics. All right. So we'll go neovim, not vim, vim, and inside static, we add a line like use use what? Use create adder. Shit. Use create then adder adder. After that, remove all these generic, functions, things, everything. How about removing this too? No, don't remove it. Inside this, instead of ampersand t, we say ampersand adder. Shit. Use create adder and then we did this actually. So we have use create adder and then we took the reference of adder. That's what we did. Then we benchmark it again. Let's go. It's clean. Let's try running it anyways. Let's try cleaning it and then running it. Go in, but still won't improve. It still won't improve. Hmm. See, dynamic dispatch is like one third times faster. What should we do? We again dump it and take everything to GPT. Hey GPT, do something. Do something. This we get we dump it. Report numbers. Now you're measuring direct call versus indirect call. Let's go. Concept check before you run. I already ran, so no need to check. Excellent. This is real system puzzles. The numbers, which is dynamic, is 33 times, which is one third times faster. Why the hell is this? Now this is counterintuitive. Yes, exactly. Now, so we reason carefully instead of guessing. Step one, what we are actually measuring. Both loops are identical except except compute is identical except what? This is static, which is engine add-on. Engine is ampersand adder. This is ampersand dynamic compute. This takes this, which is compute. Important that inline never prevents inlining the both cases. Inline never prevents inlining in both cases. So now the static path, which is direct function call, and dynamic path, which is indirect function call by a vtable, yet dynamic is faster. So dispatch is not terminating. Something else is happening. Real root cause, look carefully. X is a black box, which is I as I64. Now, black box is an optimization barrier. It inhibits certain compiler assumptions. Now, consider static state. The compiler knows engine and adder, but since compute is inline never, it must perform a normal call, possibly respect calling conventions, possibly spill register differently. So, dynamic case, the call goes to a vtable, load function pointers. Here's the key. Indirect calls sometimes produce more stable register allocation in tight loops. Why? Because the compiler does not attempt aggressive inter-procedural optimization. It generates a simpler loop body. In contrast, static variation may try to optimize around the known type, insert extra moves or spills, and generate slightly worse register allocation. Now you're observing a code gen artifact, not a dispatch cost. Now, this is why serious benchmarking uses cargo ASM or perf. Now, hardware counter or criterion.rs. Critical insight is dispatch cost, which is 5 cycle, is tiny compared to the loop overhead, black box barrier, branch prediction, register pressure, instruction layout. So you're measuring code layout differences, not dispatch overhead. Now I test you understand. So we don't improve it. Wow. Wonderful. Wonderful. How about I try to improve it myself? Do I know what I'm doing? No. So why I am doing? Because I want to. Let's go. Change the x. Instead of x, I just replace it with 2. Not this 2. We say 2 over here. Then over here, we replace it with 2. So it becomes a normal case. And then let's get a dynamic dispatch. Where are you? Over here. So we GCC it. No black box is used. No black box is harmed. Replace it with 2. We yes. Now we clean it. We run it. Let's see. Just the warnings. Just the warning, guys. Because we didn't use black box now. Please, please come on. Now what's happening is static duration is taking 177 nanoseconds, whereas dynamic duration only takes 33 nanoseconds. How about we go and check for the bin and dispatch benchmark. Let's see what are we doing over here. Are we doing something stupid? If we are, we shouldn't be. Black box, result static. Shit. Duration static, then start dot elapsed. This start dot elapsed. Duration static, duration dynamic. How about we take, more than just million? So how about we add 10 and a zero to it. Now let's see, does any magic? Large data side, large data size, so magic must happen somewhere. Nah, static duration is taking more time than even dynamic duration. So I think there is some wrong implementation going on for the. What are we doing? What are we doing? What are we doing? Mhm. Run static, add a iteration. How about we rename this static start to something like static start s, and then over here we do start s, and here we do something like start appended to d for dynamic. Over here we do something like d. Everything is changed. Run dynamic, run this. Shit. Dynamic exec, run dynamic, dynamic static exec, run static. Um, see dynamic exec looks something like this. We don't use so GCC compute. We do use, so nothing. Just use this. And what's next? Compute, run dynamic. We are designing run dynamic over here. We are telling engine to take compute and reference of compute and iterating over it, and we have everything is the same. Returning it. It looks good to me. How about static? In this run static is also taking. Acha, it's taking adder. Now what is adder? Where have we defined it? We have defined it somewhere in the compute.rs, I guess. No, we have defined it in somewhere. Where have we defined adder? Adder lib.rs. So if compute for adder, but where is the adder? Over here. Public structure adder. What is the adder? If compute for adder, then inline never. How about we just remove this inline never? GCC. Huh? What happened? GCC. 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 Why is nothing happening right now? And care. Yes. Now static duration is less, but they both are in nanoseconds. So I guess we are getting it wrong, but still, I am happy that now static duration. Ah, shit, shit. hmm Compute is this. hmm And using compute and dynamic exec. What are we trying to do? Nothing. And errors, we have overflow, invalid input. We have never used any one of them, so doesn't matter. Inline never. Over here we are using. Let's go first of all. Let's go over here. Remove this. We come up here. We insert this underscore. Does that make the change? No. Do I hope it makes the change? Yes. Over here, let's do something nice. For GCC, it is lib.rs. So let's do it. Mod compute. This uses compute to make use of src compute.rs. Use mod compute in this file to declare the module. We will, we will, we will, we will. GCC. Anything else? Anything else? Yeah, there is. We are using dispatch, dynamic exec and static exec. It could not find these. So let's go in lib. There is dynamic and there is static. Let's do 2GCC. Not here. 2GCC. All right. Let's go back to this. No errors, no warnings, no nothing. Let's see. Shit. Let's re-implement everything that we undid. Let's try, running this first of all. Let's see what happens. What is this black box? See no errors. Hmm. Static result is this. Dynamic result is this. Static is taking damn too much time. Dynamic is taking very less time. Let's count the zeros. 1, 2, 3. 1, 2, 3. 1, 2. 1, 2, 3. 1, 2, 3. 1, 2. Yes. Both are the same. What is happening right now? I don't know. I don't know. Release was optimized. The release profile optimized. Ah, what is this? Let's read it. This is the cargo book. All right. Let's see. So there is profile dev. The dev profile is used for normal development and debugging. It is default for build commands like cargo build and used for cargo install debug. The default setting for dev profile are something like this: opt level 0, debug true, split debug info is this, strip is equals to none, debug assertion is true, overflow check is true, LTO is false, panic, unwind, incremental true, code gen units 256 are false. Now, release profile is intended for optimized artifacts used for release and in production. Now, this profile is used when dash dash release file is used and it is default for cargo install. So, the default settings for the release profiles are these. Mhm. Then there are tests. So test profiles and the default profile used cargo test. Now the test profile inherits the settings from dev profile. Now the bench profile is default profile for cargo bench. The bench profile inherits the settings from release bench. The build dependencies to compile quickly all profiles by default. Do not optimize build dependencies using build scripts, the proc macros and their dependencies, and avoid computing debug info when a build dependency is not used as a runtime dependency. Now the default settings for build overrides are these: profile lev build override, opt level is 0, code gen units 256, debug false. All right. Now custom profiles look something like this. LTO true, the profile flag can be used then, but we are just using. How about just say cargo install? Cargo install error. Okay, go back. We say cargo install. What? Using cargo install to install the binary from with package. It's no longer supported. Use cargo install path instead of who build. Build the package. path this install ls cargo.toml. Let's swim into it. Cargo.toml. Let's see. We use a default profile release. What is it? LTO is false over here, but we have a true. Code gen is 1 and code gen is 16 over here. Opt level is 3. Opt level is 3. So how about just use this one? Let's go. Come over here. Use this. Remove all these. dd. We quit. This. Ah, shit. What does it say? Profile duplicate. Let's see. Yeah, it has file duplicate. Let's end these. Ah, yes, 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 yes. Let's run it again.
Yeah. Now the static is taking less time than dynamic duration. So there was some error with our cargo.terminal. So let's give it to ChatGPT. This is a happy news for us. This is very, very happy news for us. Let's go. Let's go. Let's go.
So let me tell it. I used the DFAULT cargo.toml with PROFILE profile. Profile what? Profile what? Profile, not release. Dot RELEASE. Let's give it a time, some space, and some inputs. I just used the default cargo automation profile with uh, profile release. Let's cat our own cargo automation. All right, cargo automation. We copy it. We will paste it. Okay. Now we'll dump using pdump p everything. Let's go over here. Let's put it. Yes, I did it. I didn't understand what I did, but I got the point that there was no error with our code. But what is happening was some optimization. And who does the optimization? Will Cargo does. And we had you removed the black box, generic and static path, result, LDO, Strauss module, aggressive optimization. You increase the iteration to 100 million and you get this. Now the static is faster, difference is 46 milliseconds, 17 to 18% slower for dynamic. This is realistic. We finally isolated the dispatch cost. Yes! What changed? The current loop is something like this, like the initial one. Now, no black box, no input variability, no branching, no generics, no LTO. So compiler generates static, which is direct call instruction. Dynamic does what? Loads the vtable pointer, loads function pointer, indirect jump. That indirect jump costs the branch prediction plus pipeline effect. At 100 million iterations, the overhead becomes measurable. What you just learned, very important. Dispatch cost is tiny per call. It becomes visible only in extremely tight loop. And compiler settings massively changes result. LTO can distort micro benching, and black box changes register allocation. Code layout affects performance more than dispatch sometimes. Now, this is real system engineering. I don't know about you, but about me, yes, I did it. So, question one, don't ask me questions, just praise me right now. Right? Why did removing black box allow static to fully outperform dynamic? Uh, well, it was not the FAULT fault of BLACKBOX. I think it was because the LTS was false or was true. What was that? Let's cargo it. Let's see what was the LTS right now. LTS is false. LTS was true. That sort of over overcompiled. No. What is that word? Over simplified? No. What it did? LTS. What it does? LTO. What is it? LTO? Yeah, LTO, not LTS. because of LDO, over optimized, sort of over optimized. That's what I think. Why did removing black box allow static to finally outperform dynamic? The real world code, which is web server databases, would dynamic dispatch overhead matter? No, no, just milliseconds of time that we get after over optimizing can become optimizing, optimizing, optimizing. No, just few milliseconds of time matters. That's why I didn't wrote that it doesn't matter. But over optimizing can become the problem. So just lightly a bit of overhead because of fat pointer, the data, PTR, and the tables DOESNT matter. Well, it matters when you are doing the SIMPD, isn't it? You are optimizing for CPU behaviors and all that. Yes, then it matters, but not in the real world, like making web servers, making databases. Not then. If this loop were doing heavy mathematics, what would happen to the 17% gap? It would increase. It would increase. This is good. This is better. I don't want to propose change. Sorry. PD level 3. LTO true. The LTO setting controls the Rust's C LTO, which is linker plugin LTO, and C embedded bitcode options, which controls LLVM's link time optimizations. So LTO can produce better optimized code using whole program analysis at the cost of longer linking time. The valid options are true or fat. Perform fat LTO, which attempts to perform optimization across all crates within the dependency graph. Thin, which is perform the thin LTO. This is similar to fat but takes substantially less time to run while still achieving the performance gain similar to fat. Now, false is performs the thin local LTO, which performs thin LTO on the local crate only across its code chain unit. No LTO is performed if code chain unit is 1 or opt level is 0. Off is disable the LTO. Panic, then incremental, and there's R path. So the R path setting controls the C R path flag. What is this C? Is it the real language wala C or what is this? Which controls whether or not the R path is enabled? Or does this C means control? What is this C used for? Or is it for cargo? I don't know. So this was our phase 4, isn't it? So this this was a phase 4. So let's see what was the task after phase 4. It was something related to Python, I guess. Error modeling. So we wanted to error model. So modify trait to do this and that. And phase 5 would be the unit test, which is lib.rs and cargo test. Unit test, which is 30 to 45. Yeah, that was there by default, I guess. So let's just copy this and let's go to penguin lib.rs. Where is it? src lib.rs. Now do what? Let's just take a line, implement the test. Do this. We go like cargo tests. What is it? It failed. Unwrap method not found in. Where is it? Lib64. 23. 23. Unwrap method is not found. Why happened? I removed it. Yeah, I removed it. I removed it. So why not just remove it? CW, remove this. We don't need you. We don't want you. Let's test. And everything passed. So test is test add okay, test result okay, test result okay, dot test. So what do we get? Make a tree. Oh shit. Yeah. This is everything in target, This is targeting our target. And these are all outputs. Compute engine, GenX, what is that? Dispatch bench. Everything has so many sort of outputs and binaries and log and whatnot. Oh, there's D also, is it dependencies or something like that? Nice. All right. What is this cache directory tag? You don't need it. You just clear it. We'll go and ask ChatGPT, what's the next step? What do we do next? And I will take a break a little bit. So you removed black box. Yeah, I did it. Incorrect. What is Acha? This is incorrect. You answered it was LTO, not black box. This is incomplete and partially wrong. Well, I am right because you were wrong. Correct reasoning would be that black box prevents the optimizer from reasoning out values, and when present, it disrupts the certain optimization and affects register allocation in tight loops. That distortion can dominate dispatch costs. So LTO also affects things earlier, but in the final experiment, the decisive change was removal of black box. So removal of generics, removal of results, complete direct call. So correct conceptual answer would be that removing black box allowed the compiler to generate a tighter loop with better registers and allocating or exposing the true dispatch difference. Mostly correct, but imprecise. You said few milliseconds doesn't matter. That's shallow. Well, I am shallow. And you have full depth. That's why you couldn't do it. Now, the correct reason is the dynamic dispatch overhead is 3 to 8 cycles per call and negligible when each call performs, meaningful work. Only relevant in hot inner loops. Correct is that in real system, the dynamic dispatch overhead is negligible unless it occurs inside extremely tight performance critical loop. This is also incorrect. Why? You answered A. Gap increases. It would shrink. Why? Because each iterations did heavy math, which is let's say 200 to 500 cycles. Then fixed dispatch cost is about 5 cycles. it becomes much smaller fraction of total work. Relative overhead decreases. This is fundamental performance modeling. So now core performance principle is like overhead percentage is fixed overhead divided by total work. And if total work increases, the relative overhead shrinks. Now we close the dispatch topic. Now we understand monomorphization, inlining, L2 influence, code gen artifact, micro benchmark pitfalls, and dispatch cost reality. Now this is deep system level knowledge. I don't know anything about this. Let's say we move to something more important. Error propagation architecture. Now we have to do this again. I don't want to. We have to. So we return to this. Now we build it properly. Concept one, error is a type boundary. So well, you answer it. I'll go and take a break. Yeah. So these are your questions. Hello, hello, hello. We are back, and let's first of all finish this first, and after that, before starting the Python, I might take a break again. So this is now why is result TE zero cost in success path? Because it uses heap allocation, because it is tagged union compiled to simple control flow, because it is dynamic dispatch, because errors are ignored. One T. In success path, there is no error. No? So I think error gets ignored, so it is passed. Now two. What is two? Why is unwrap architecturally dangerous in libraries? One precise answer. Because it doesn't handle errors gracefully, but just returns or exit the program with an error. So this is the biggest downside that I can think of because of unwrap. Now, when designing an error enum for library, what should it represent? So, when designing a enum library, enum, sorry, when designing an error enum, so enum for errors, yeah, like we did for overflow and all that. For a library, what should it represent? All possible runtime crashes, yeah. Only failures that callers can meaningfully handle, yeah. Internal panics, voice signals. B seems the right answers to me. All possible runtime crashes is not possible. This is incorrect. Third one will be incorrect too. Let's see. Third one was correct. Wow. So first one was incorrect, and you answered D. Errors are ignored. Yeah, but it is because the result T is tagged union of an enum. In optimized build, the success path is just straight line code. So the compiler lays out, results efficiently. The benchmark prediction makes the OK path extremely cheap. Again, the success path is just a straight line code. So the compiler lays out the result efficiently, and branch prediction makes the OK path extremely cheap. And no heap allocation, no hidden stack unwinding like exceptions. So the zero cost means you only pay for error handling when an error actually occurs. So now that errors are ignored, not that errors are ignored. So what is the answer? B, because it is tagged as union compiled in simple control flow. Who knows what it means? So yeah. Now question two, partially correct but imprecise. You said unwrap doesn't handle error gracefully and exits. The real architectural issue is deeper. The unwrap converts the recoverable error into a panic, violating the error boundary contract of a library. Yeah, that's what I mean by untimely exit of a program. You shouldn't be doing that if you can handle it gracefully. So that's what I meant. Libraries must never decide to crash the process. The decision belongs to the application layer. Now, question three was correct because error enums should represent failures that caller can meaningfully react to, not internal invariants or impossible states, not the programmer bugs. Now we go deeper. Concept is error boundary. So in Rust system architecture, leaf function may return a detailed error and internal modules may map errors. So public API exposes a clean and stable error enum. This is deliberate design. So exercise, design a proper error architecture that we had designed earlier. Define error.rs, something like this. We rebuild compute engine properly. All right, we do. Let's inside that get into SRC, open up nvim. Inside library, there exists a pub mod errors. So gbc. Now inside, errors, dismiss. Inside errors, just go back, invalid input, and we are also seeing something like division by zero. So let's add that also. We get a O, which is division by by z zero. So for now we are just adding it, so doesn't matter. Now this is computer error. All right, compute error, not computer. Then step 2 is for trait. Now we do this. Good. We go to trait. Where is this trait? Over here. We'll make the things. First of all, use this. So GCC. And now we'll go like, instead of returning I64, give us, you know, compute error also. So com compute error, isn't it? We are getting compute error. RESULT result and compute error. So trait is finished. Now add a divider. Where? Where should we add this divider? Compute for divider. Uh, where we have added, compute for add, there only we'll add this divider also. So where have we added, compute for add? Run dynamic, no. Over here, no. Yeah, compute for, adder. Over here, we'll use compute for divider also. So static, no. Over here, we have to go like this. And I am saying something like use create adder. We shouldn't be needing that now. We must make it like A or T, which is of type, you know, uh, it compute, COMPUTE, ampersand compute. Let's say ampersand compute. And instead of doing this, we go like T. Is it correct? Will it run? Uh, let's try. Let's try. So cargo, array, whatever, cargo test. This result, TE, not implement partial equality. What else? Shit. We have to make it proper, not just compute the. This seems correct. So let's now move on to dismiss this. Is this correct? We don't care. Computer, this is correct. And now over here, yeah. So instead of making these changes right now, let's wait for some time. Let's wait for some time. And let's do something like, instead of returning this, we should be returning result I64, no? Let's read it. Before divider, is there anything else you want me to tell? No, you don't want me to tell anything. Shit. You're stuck again. How can I just go back? So I guess I only implemented it in compute RS. So let's just go back, go back, go back, go back. Let's just start from a new. So if cargo test, does it run? No, it doesn't. Why? Method is not found in header. What happened? What all did we change? Did we change this? Yes. Now what? Uh, no. Dispatch. Did we change this? I don't think so. Do we need to change this? Let adder is equals to adder from here. Then we have to also call, the divider like that. Let's not focus on that for now. We have bigger problems in front of us. Uh, computers. Shit. Yeah, let's first write it. And now seems nice. This also seems nice. What is this? Good for us. Hmm. So here we describe, adder. And here what we did. So I guess now there is zero change. Now there is zero change. So let's move on. Create test. It finishes. So everything is okay. Everything is done. Now let's change, the static exec. So let's see if we can recall it correctly. We had a type generic type T, which is of type sort of compute, 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 and finish. Oh shit. Uh, yeah, compute, and either compute or either reference of compute. So I don't remember. For now, I'll just do compute and then this, which is the reference T. Now let's go back. Let's run cargo test. Everything finishes. So I guess, we are back. So instead of saying adder, we can now use directly. If we don't use GCC this, we don't use this, we are still good to go. Quit this here, quit this, escape, escape. We are good to go if we don't add this cargo test. Yeah. So let's remove adder from everywhere. Let's try removing it. All right. There is no adder over here. Over here, is there any adder? There is adder. So what is adder? To what is adder? So we are using compute engine and adder. So from here, we are using adder. Do we really need it? Let add. Yeah, we do. We do. We do. So instead of adder, let's make it, generic. So instead of passing, adder, we should pass compute. So compute what? We say compute is type. Uh-huh. So let's not change anything except this line over here, because adder is only used by this, Now instead of going there, I just say CW. What if I just say COMPUTE? Compute. What now? Will it work? It doesn't. It says not found in this scope. Okay. So we'll change it to some generic type or something like that. Where are we? So use compute, then compute, and inside then we are creating public structure that's called adder. Why are we creating it? For compute for adder. What do you want to, compute for generic type? Ah, let's not do that. Let's do something like, nah. First of all, solve all the errors that are there. Is there any errors? I think so. It run static takes the type T, which is compute, and it takes its reference T, instead of directly taking the adder. So dispatch, and over here, what if we just say type T, generic type T? Not found in this scope. We'll make it found. Cannot found this T scope. Could not compile compute the T. All right. We will make it happen. Dispatch benchmark. Here, if we try this, that T is shit. T is type. What is it? Compute engine. COM, not compute engine. You are taking adder. You can also take divider, and we shouldn't be needing that. How is it? Compute, or just this escape. So there is dynamic exec, run dynamic. Uh, this is unused right now. I expected an identifier. Let's see. Compute for adder. Two. So this is capital compute. Let's do that. Not dynamic, but dispatch. How about we make it capital C? And why is it just T iteration? Shouldn't it be something like ampersand T, then iteration? Expected identifier. What is the identifier? T, and engine is ampersand T. So let's just make that happen. Fix it. CINE is this run should run dynamic is in this. Let's try this first of all, which will not work. I know that, but so I tried it. Now let's just make it, what it was. Ampersand adder, ampersand adder. Now this will work. This squared test. It passes. Now I want to see if we make it small c. Will this still work? It shouldn't, but we'll see. What the hell? What the hell? There are so many things happening right now. Yes. There is an error. What does it says? A trait with similar name existing. Notice capitalization. So it says it is capital C compute, and that is the trait. There is a trait capital C wala compute. Replace this with capital C. Oh, capital C. Oh, shit. Side capital C. This is the trait, and we take the self, which is adder, divider, whatever. So over here we say compute for adder. So it's like it takes the self and gives you a plus b. So the compute for divider will take the self and give you a divided by b. There's nothing wrong with that. What's wrong is we are not able to take directly just the compute. We have to take adder. Why? Nobody knows. So quit it, make it, save. Now what I want to change is create compute. All right, we now know this has a create compute create compute engine. How about we just use create compute and we gave it a compute instead of adder. Shit, what is it? GCC. Over here, take a line. We say C use create CMP, not this, compute, then COMP. CPU compute. COMPUT. Use compute. That's what it was used, no? Where was it? Compute. And then does use compute. Alright? Not create, just used compute. Acha, over here it's create compute. So let's try. First of all, use compute. First of all, use create compute, and then this one. Now, instead of passing the adder, we will pass directly the type T, which will be compute. Damn it. COMPUTE. Create compute, and instead of passing the adder, we pass a type T, which is of type compute. Now there exists a type compute, and instead of sending this, we'll send type T, which will be, yeah, I think this should pass. It doesn't. So what does it says? It says compute unresolved import. A similar path exists, which is compute engine compute. So use that. All right, use that. So instead of using this, we'll use that. Are we getting any other errors? I don't think so. So we'll do this. We'll use compute engine and inside that compute, and after that, whatever we were doing. Okay. Oh yeah, this is good. We want to change this to paste compute, and now if I say use COMPUTE, all right, and use, and I just comment it out, GCC, yeah, use compute engine compute. Oh, will it work? Will it work now? Nah, it says identifier, expected identifier. What is this error? Uh, must answer me. What is this error? Because I am getting it again and again. I know that we are doing some mistake, but still, let's ask. What is this? Now we debug properly. Your line result dynamic compute. Compiler say expected identifier found this. You did nothing wrong. You tried to write a generic constraint that at the call site. This syntax is only valid in function definition in implementation blocks in trade definition. It is not valid when calling a function. Rule is that generic bound belongs in definition, not invocation. So this is not good. Example valid is all right. So this is good, but example of invalid at call site, this is not good. You cannot declare the trade bound while calling it. Correct way to do it is if dynamic, then do this, then call it like that. But it is not. So we are calling adder, right? If it was generic like this, then simply call the adder. The type inference handles the T. If needed explicitly, run dynamic adder and then adder. But I want to, but now we have adder and divider both. So what do we create to whatever we are going to create? Excellent question. Struct adder, both implement the trade compute. So you ask, do we create to what? To dispatch path, to function, to trade implement? No, this is we have to implement it. Dispatch path, I guess. No, we do one abstraction, one multiple implementation. This is entire point of trade. This is good. You implement adder and divider. All right. Now the dispatch version. If you want static dispatch, it says compute and engine is ampersand t. This is this. Uh, then while calling, you have to use adder and divider. All right. All right. All right. So now we know we have to. So good. Good for us that we stopped at time when we had that. Dynamic dispatch version is this. We have to call adder divider, or even just adder divider. But right now, what are we doing right now? Not this, this. Uh-huh. How are we calling dynamic one, two? Shit. Oh, I have to undo everything. GCC. So now if we have adder and divider both, we'll just add divider over here. divider. All right. We'll say this and we quit. No divider in the root. Yeah. For now there is not. We'll make it. So this is compute run static, which is computing and doing all sort of stuff. Uh, Over here, we did it in compute. Let's not for now. Okay. Now we go to lib and we create or implement sort of instead of adder, we now also have public struct for divider divider, which will go like this. We'll implement compute for divider. Then we'll say something like whatever this is, inline never, no, never, never, square brackets. Then we'll say fn, which is function compute. We'll send the self, which is now divider, HSELF. We'll send a, which is again I64. Do we have to mention it every time? Because it is already known that it will be I64. The result we'll be getting for now is again I64, but we want to implement, the result. So we'll implement the result I64 and compute error. Okay, we get compute error. What else? Now we implement. So if b is equals to, oh shit. Now a and b cannot be I64. It should be F64. F64 because it is float. If b is equals to 0.0, then what? Then send error, which is like b is 0, else do what? A divided by B in OK. Okay, inside OK, big one. As for here also, we'll implement, you know, A, if there is result, which is I64, and then compute error. Then we go like, OK, delete this. A plus B. So I guess now we have adder, we have divider. Uh, let's check the result. Uh, yank 2K. Now paste it. Now what? Instead of saying adder, let divider divider is equals to divider, and then we say divider dot compute divider dot compute. Sorry, we say like cw divider dot compute this divider, and we send 2.0. Let's send 5 and 5. So 3.0 and 3.0. This seems better. You can get 0. Let's see 9. 9. Full division. So we will expect something like 933, 3.0, 3.0. This is our expectation. This is our test. Now there are adder and divider. So let's see. Here it is adder and divider. Do we have anything like this in compute.rs? Yeah. In dynamic, it seems good. Static looks good. Lib we defined. Yeah, error should be something like division by 0, isn't it? For now, let's see librs again. Compute error. Compute error goes something like, insert divi alone by zer, division by 0. So everything looks good. I think over here also I have to say, compute the result. So I guess yes, I have to say like RESULT and UMPUTE ERR compute error. Now this is good. We say compute save. Compute is good. This must be good. Nah, it is not. Why not? Because it is still expecting after compute and all result of I64. It can never get I60. Result I64, which is of type, again, what is the type? Compute, you know, ERR. Mm, all right. After this, you have to return something. Instead of returning this, you have to say okay, then return this. Same for static now. Static, yes, I result I64, comma, compute EERROR, error. Now instead of sending ACC, uh, we have to send OK and this ACC. What else? So dispatch is there. Dispatch is good. Compute is good. Dynamic RS is good. And error, I don't think this is good, but still, compute error is there. We have not implemented overflow and all things like that in adding, but yeah, like add should happen like level also good. Steady. I can't see much of an error now because I don't know. So let's save it all. Yes. What is it? Test, cargo test, assert EQ. Result is IFO. Compute 64. It is because of float. Yeah, now I get it. But for division, we have to use float, no? So now instead of everywhere, wherever you see I, we have to create F. Even U, we have to create them to also to. So we have to create it 2.0, about 3.0 over here instead of U64. How about F64? And now anything else? Not here. So we'll say okay, good. Now we go to dispatch over here also. Is there anything that we want to send? No, this is just dispatching. So compute RS, wherever we see I, we replace it with F. Wherever we see I, we replace it with F. Wherever we see I, we replace it with F. This is good. Save it. Compute is done. Dynamic. Wherever we see I, first of all, at least input a float, then we can do whatever we want to. Wherever we see I or U, we convert it to F. Wherever we see I or U, we convert it to F. We don't want integers, we want float. We want float. We want float. We don't want integers, we want float. This is done. How about this? Nothing to be. Over here. We want justice. We want justice. Not justice, but yeah. Replace it with float. Replace it with float. Replace it with float. Now what? Is there anything else? 0.0, P is 0. over here. Instead of getting 5, we'll get 5.0. Instead of getting 2, we'll get 2.0 and 3.0. Add up. Anything else? No. What is left? Static exec is left. Wherever we see I, we have already made it F. Instead, we have a result left over here. So replace, sorry, not E, word back, replace it with F. Yes, 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 yes. I think save changes. What's next? Cargo test. Uh, Result is F64 and compute error float binary operation equals to cannot be applied to type result F64. And what else? Enum result T and E not implemented. Okay, okay. We'll implement them. What else? Okay. Is this argument influences the type of okay. And expected I64, found F64. Oh, did it? Where lib.rs, no? Let's go to lib.rs. When lib.rs, did it expect something like, yes, yes, I got it. I got it. So let's do something like this. We say cat and we say everything. Then we grab something like I64. We don't want to see I64. So we still see I64, but those both are common, so no need to worry about them. Now at least one error should have been gone. Yeah, I don't see. So division by 0 was not what it expected. Unexpected argument. So let's remove it. As for OK, this argument influences the type of OK. Expected F64 found integer. In static exec. Let's see. And given static exec F64 %t compute. Where is it getting I from? Nobody is giving it I. Is there any number? There is no hard-coded number over here. In here, I don't see it. Then here, I don't see it again. Errors. Database. Let's remove this because this is also creating some problems. And let's not implement any test for this. Just GCC. Why is that? So GCC, GCC, GCC. What now? Is there anything else you want us to know? So it's just that result is not yet implemented. So we implement it. How about that? We'll go in result, not over here in lib. We will create lib. All right. We say somewhere over here, we say result is this and close this. Then we say, oh, What do we say? Uh, he said there exists a type called OK, and then what? Nothing. And there exists a type ARR. All right, is that it? Cargo test. Now, not implemented. I just did. I just did. So shit. I don't think I can solve this. Oh damn. How many lines of errors are there? Shit. Somewhere it's not use error in lib.rs, in lib.rs, in static.rs. All right, we'll just do this. All right, lib. Oh shit. And let's start. So let's use it. All right, not much of a problem. Save it. We'll go to dynamic over here. We'll say use it and save it. We go to somewhere lib.rs. We'll say use it and don't remember us. Just go away. Shit. Not this. This. Right? Oh, keep some gap. Save it. All right. What's next? I don't think I can see any more errors. Did we reduce some number of errors? Not even reduced. Integer plus equals to result. 64. Shit. Now we have only one thing to do, that is pre-dump everything to our GPT model. Uh, I am getting many errors, so help me solve those errors. Aha, shit. Did we not do speed up? Do speed up. Now take a line, print everything. So error one is for I in 0 to iteration with, iteration is F64. This is the error. Now error is for, shit. So error is for I in 0 to iteration, with iteration being F64. You wrote something like this. I made iteration F64. Damn it. Damn it. Shit. Just mindlessly changing everything can break most of the things. So iteration should not be F64. It should be just U64 or whatever it was. 2. Just use J. Come over here. Go back. Replace it with U. All right. Save it. And when dynamic, again the same problem. Iteration should be U64. How about that? Now, what happens to your test? Hmm, still there. Is it less? Is it more? Still there. User create. So static exec. Did I not introduce this? Yes, let's copy this and go to where would I want to go? Static exec. I introduced it, I think. I think I did. No, I did not. Sorry. I did not. How about now? Cargo test. Do I see that error again? No, I don't see that same error. All right. Now, what's next? Fix is youth 60. I just did that. I did that. Error 2, you are adding result to F64. Yeah, inside this loop, I am doing this, but compute is result F64. So you can just do this. You cannot just add result to F64. What you must do is ACC. What you must, where is it? Propagate error using this, which means the function must return the result, something like this. The part is already correct in signature. Fix is that I should just, use question marks. So let's go and use question marks. Is it this? Yeah. So let's add a question mark at the end and save it. And then let's go to dynamic. Where is it? Let's go to dynamic iteration J. So insert a question mark. That's it. We're good to go. Not very good, but still. Still, there's too many errors. Fix is that do this and the function must return result. That part is already correct in the signature. Error 3, wrong error type in divider. So error B is 0. That trait requires result F64 and compute error. So error must be compute error and division by 0. All right. So error should look something like this. Instead of B is 0. All right. Error is not implemented over here. Is error? No. 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 Over here. No. Over here. I guess so. Let's see. See what is implemented and how it is. Yeah, over here. So it should not be anything like this. Where is this? Oh, COMPUTER error, and inside that we get division by Zero. All right. Now I think this is correct. Division by zero. Division by zero. Division. Division. Compute error. Compute error. Yeah, I think this part is now correct. Let's save it. End it. Try testing it. What happened? Do we see that error? Implementation. We don't. We don't see those. All right. Now next, what is it? So error must be this. Error 4 is ACC type mismatch. So let mute is equals to ACC is equals to 0. So compute returns F64. Now ACC must be F64 or 0.0. So ACC must be 0.0. So where is ACC? ACC must be 0.0, which is sort of F64 to F64. Print this. Is it good? I think so. Over here? No. Here? Yes. ACC must be insert 0.0 and it must be type of F64. What's next? ACC is 0.0. Dynamic. Just save it. Save and quit. Cargo tests. So error reduced like quite a lot. So now I see assert, then I see this result and the result static, and I see some mosquitoes. Hmm. So it doesn't implement, display. So we can use derived debug for that, or we just don't use, print. After all, you don't need to print. Type mismatch. ACC is fixed. Now error 5, test incorrect. What is that? You wrote let result is equals to add compute this much, then result is 5.0. Now the result is this type. So it is type result, then F64 and compute error. So you must unwrap or match. How about unwrap? So test may use unwrap, library code must not. All right. So let's introduce that test in the lib. We go in lib, and where are you testing? We're testing over here. Paste it. Delete it. Shit. Delete it. Delete this. Yeah, go to cargo test. Yeah. So now there is just these two. The corrected code is this. I'll see that in a moment. For now, why must iteration be in integer type? Not right now. Let's first clear some steps. So in dispatch bench, dispatch and not dynamic. You have to go in binary and then the dispatch bench. You have no implementation for result static, so just don't print it. Damn it. Now we don't see any error. Yeah, everything is running well. When we run cargo cargo. Build. Did we use build or run? We used run, no? And we say release, and we say bin, and we say dispatch. What was the name? What was the name? Dispatch ls, bin dispatch bench.rs. So dispatch dispatch benchmark. Damn it. Dynamic is slower by a very minute difference, but it is slower. Now what is it telling me? So I am going to take some break, and now I am going to create a you know corrected version of compute engine. Cargo new CORRECTED corrected version of compute ENGINE with all the operations. So now give me step by step each file and codes needed for this corrected version. No experimentation now. All right, I'm going to take a break right now. So let's meet in few minutes. So I'm back. So we left somewhere where we told the chat GPT that we are going to now create a new, you know, sort of corrected version of compute engine. LL. So we have a compute engine right now and we want a corrected version. So we are going to, start a new cargo. So we'll say cargo, and we'll say new and corrected version for compute engine, ENGINE. All right. So it has created. Now we must see what is there in cargo.toml. All right. So we only see these, but we want the earlier cargo toml only. So we'll see what we can do. All right. So first of all, step one is to do this and get into the corrective version. Now the final project structure will look something like this. All right. So let's make it. happen. Let's go into CORR corrected version. Now we are seeing SRC. So let's get into SRC. Now we have lib.rs, compute.rs, error.rs. So let's create all these rs. Right. Copy these, paste it over here. Aha, it's very slow. It's hanging too. So this is dynamic. Uh, Operations. Right. Then here. Errors. Then we will finally go to lib.rs. rs. Home, and we'll say touch. Touch creates it. So yeah, we select all, cut it from here, go to our terminal, we paste it, execute it. We can now see we have all the files. Now, what else? In binary, we need main.rs. So, and we'll say bin and create main.rs. Will it create it? Oh, sorry, shit. Quit. Uh, Quit anyways, yes. Inside binary is a directory, so like this. Now save it. Now if we see the tree, it looks something like this. Yeah. Now step 2, we create the error.rs. Looks something like this. Let's do it. We'll go nvim, not nvim right now. We'll do vim error.rs. All right. We'll say that this is something called src, and inside that we have error.rs. All right. And now what are we doing is we're first of all telling it to de derive debug. Yeah, derive debug, derive debug. We'll go fast. Public enum and computer. COMPUTE, compute error. So compute error. All right. Overflow, division by 0, invalid input. So there is overflow division by 0, and then invalid input. Is it correct? Seems so. Let's move on. That's why I was saying errors. All right, all right. I didn't understood it, but it is telling me there is some error. There is no error. Now step 3 is create compute.rs. So we'll create compute.rs. Vim, not sim, we'll say vim, compute.rs. Inside that, we'll say in a comment that this is src compute.rs, and inside that we'll say that use what? Create and compute. What is what? Create error. Yeah, crate, create error. Then compute error. All right. Semicolon, and we move on to public trait, then compute. Inside that we are creating public, first of all, trait. Inside that come public trade compute. All right. And inside that, what are we doing? We are creating a sort of method for that trade, which is again called compute. And inside that, we are passing it using ampersand self self. Then we are passing a, which is type of f64, because we'll be dividing also. So f64 is our type. B is also f64, and then the return type will be result. All right. So return type will be result, result. Inside that, we'll have f64, and we'll have compute error. All right. Oh shit. Compute error. I can't just accept it. I have this suggestion, but I can't accept it. Vim, I don't know why. I have to ask how to set these suggestions. But this is it. This is our trait, and that's our method. I think we did no mistake. Uh, did we? No. There's just an extra space that I don't like seeing. So we'll remove it. And compute. Spelling seems nice. Everything seems nice. Nice and clear. All right. We'll save it and we'll move on. Move on to step 4, which is operation.rs. So we'll create operation.rs. We'll take compute and compute error. All right. Vim operation.rs. Inside that, we'll first of all insert. Then we'll say src. Then we'll say operation.rs. And inside that, we will use compute, and we want use compute error, but we have to define it. So we have to say from create. See, for create, we have to say error. We have to say this compute error, isn't it? Small error, small error. So just, I know. Replace this with small error, and we go over here. And we again say that for create compute, we say create and small compute. There exists a trait that is compute and semicolon. Now we'll create adder, subtractor, multiplier, and divider. All right. So inside operations, we'll create all these public structures. So pub adder. All right. Sorry, pub struct adder. That's what I was thinking. There was something wrong. Pub struct, pub struct adder. Is it correct? Yeah. Now we'll implement compute for adder by saying this. All right. Now we will implement compute for adder, adder. How? We use this, which is again a method in adder, or just compute, which is compute, which was a method. We'll take the reference of self, which is adder right now, and we'll take a value a, which is f64 for now. Then we'll take a value which is f64 again, f64 again, and then we will get a result. All right, the return value will be a result, result. Inside that, we'll have a f64, and what we'll have is compute error, computererror, compute error. All right. Now this is not implemented yet because we want to say that if everything is okay, just return okay and then add a plus b. A plus b. That should happen in ideal case. Yeah, that's what happens. Now we move to what? We move to subtractor. So now we go and say that there exists something called public struct. Is there any error in these two lines? Kya or what? What is happening? Why are they discolored like this? Use crate crate compute and then compute. Then we have compute error, which is nice and good. Oh, we might not have defined compute right now. All right. So add a no, we have defined compute. What are we saying? We have defined compute. For now, we'll do something for subtractor, subtractor. Correct spelling? Subtractor. Yeah, subtractor. Now we implement compute, compute, for subtractor, tractor. Inside that, we will have the method for subtractor explained that compute should happen like this. First, we take self, which is subtractor for now. Then we will have a value which is a type f64. Then we'll have a b of type f64 again, and then we will have a return that is result result, which will contain f64 and also contain compute error compute replace with capital E. Now everything is right. Compute error. All right. But now we have to implement what happens. If everything is okay, then we'll say return okay and A minus B. All right. Is there something incorrect? Is there something incorrect about this? I don't think so. I think it's correct. All right. For multiplier, PLIER. All right. We'll create a public structure called pub struct and then multiplier. All right. We'll implement calculate implement not calculate compute compute for multiplier multiplier. It goes something like this. It'll have a method compute which will send the self first. Where is the self? Self has a value a which will log type f64, and then another one which will type again same f64. It will give us a result which it will give us a return value which will be a result, yeah, which will contain f64 for our calculation and compute error in case of any sort of error. All right, it's done. It's done. It's done. Now we just have to define what should we do. If everything is okay, like most of the time it is, we say A star B. That's it. Now I think we have defined everything except for divider. So we say struct and then divider, divider. All right. So now we implement compute for divider. Oh shit. divider. Inside that we have a method to explain. It is compute small p, compute. Beside that, we are passing first of all self, self, and then we have a, which is of type f64. Then we have b, which is again of type f64. Then we are getting a return value, which is a result. Inside that we have f64 and a compute error. Oh, sorry, error. All right. Now we explain what happens over here. So we go like, if b is equal to 0.0, what should happen? It should get an error, error, not or, which will say something like compute error, go like this, division by 0. That's what it says, no? Let me see, not over here, in error.rs. What does it say? Division by 0. Yes, that's what it says. So we move on. It says division by 0, and else we write else, else. We just give a OK value, OK value with a dividing b, a getting divided by b, so a divided b. All right, I think, shit, what happened? This file is not included anywhere in the module tree, so Rust can't. What the hell? It's not included right now, so there is no error, no, so don't worry about it. Let me create things. I think I have implemented more than enough. And divid here, right? Yeah, let's move on from this. Now what we'll do is create a static exec.rs, which will have compute and compute error. All right, static exec.rs. This is now from src, static All right, what it does have is use crate, create error for compute error. Then what? Use crate for compute, which is compute. All right, shit. Append semicolon. I think now it's right. Use crate, use compute error. Error, compute error. Yeah, I think it's correct. Now we'll create a function, a public function that is run static, which will have a type t compute, and will have engine value of generic t, and then a is f64, b is f64, getting result, then engine.compute ab. That's it. So we create a public function, isn't it? Yeah, called run static, run static. It has a type generic t, which is compute, right? Now let's w. It doesn't do anything, so let's implement more. Now what it does is it takes engine, which is of type ampersand t, which is reference of the general rate t. Then we have a value which is again same F64, and B, which is again uh, F64. After that, what do we have? We get a result. We get a return value which is type result. Inside that, we have a F64 value and a compute error. There is a spelling mistake, so let's push it. COMPUT, compute error. Is that it? No. Now we have to implement it. What do you mean by that? Well, what I mean is we have to say what happens. So you have to say something like engine.compute, engine dot compute, isn't it? Then pass A and B from it. That's what happens. It's looking good. It's looking good to me. W. Yeah, it is good. So now we'll create, I guess, a dynamic exec dot rs. We have a file now. So we go like we have a src inside that dynamic exec and dot rs. Inside that we will use crate, which will have a type called compute, which will have something called trait, which is compute with capital C. Shopee, we'll use create a crate, crate, which will be of type error, and then it will be a trait, not trait, but enum, compute error, which is again a type, a custom type. This, now we go to use it. So we create what? We create a public function called run dynamic, I guess. Inside that, we pass engine directly as ampersand, you know, dynamic and compute. All right. Then we pass A, which is of type again F64. We pass B, which is again of type F64. We get a return value, which is again a result, RESULT, which will have F64 as well as compute ERROR. It's not finished yet because we have to define what we are doing with this. So we'll say that what we'll do with this is we'll create engine dot compute, and then we'll pass A comma B from this. All right, everything seems fine to me. Let's see. Looks very similar. Oh, this is static. All right. Dynamic is still, similar. Just engine is dynamic compute. That's what we said, and then everything is same. It's just this is dynamic compute, and this is which is a generic type static compute. That's it. That's about it. So now, oh shit, what happened? This file has not been used anyway. Now we know that. We know static. Oh, static. Static has also not been used now. So why is it not getting gray? Whereas our other file is getting, now it's getting gray. See? So we have, yeah, everything looks the great. Now we have lib.rs that we are going to create. And then unit test.rs. ls-la or lh, whatever. So I am seeing there is only lib.rs for which there is 0 size. So we have to create lib.rs, As for the others, we have created them, and there is no unit test.rs. So you have to create that also. So, and as for bin, let's see for bin, not here, bin like this. It is also 0. So we also have to create the main.rs. All right. So let's create lib.rs first. Lib.rs, inside that, we'll go first of all telling it that you have an address which is src and lib.rc, and inside that we have to use what? Create. We don't use, nah, we use it, but we make it public. So now we have to use public use error, compute, and operation. As for these, like dynamic execute, static execute, operation, error, compute. All right, all right, all right. We'll make it. So first of all, we'll create public use, then we'll create public load. All right, public use, because we know that create and then small compute and then big compute. All right, this seems right. We'll create public and use, then create. Inside that we have an error. Inside that we have compute, error. All right, we are in a close, so we'll write pub. We'll use what? Use for create, CRATE for that. Or we'll use OPERATIONS, operation or operations, and small one, and there is no create. So OPERATIONS. For that, we are importing everything, semicolon. So public use operations and everything. Yeah, it seems right. Seems about right. Everything looks good. There is no crate. So yeah, whatever. We'll just remove these. Oh shit. CW and CW. We'll say delete, 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 delete. Then we have compute, error. All right. Now we'll create mod. So we'll go like public. Then we have a mod like module. What's the name of it? It has a name of compute with a missing p. So compute. Yes, that's it. We have a public mod called operations. All right. Then we have a public mod called what? Dynamic, E with a missing EXEC. And then we have a public mod mod of static 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 execute for what else error. So we have public mod for error. All right, what else? We have a public mod. Anything remaining? Is there anything remaining right now? Error is done. No, A. C is done. Compute error. Is it done? No. Compute error is not done. So compute error comes under error. So 1, 2, 3, 4, 5. How many? 1, 2, 3, 4, 5. Yeah. So that's about it. This is lib.rs. Yes. Now re-export clean API surface. Re-export clean API surface. Now there is a step 8, which is, unit test. Inside lib.rs only. Oh my God. You have to create all these unit tests for everything. So let's do it. Let's do it. Come over here. Let's get into a new line. Then what we'll say, I've never created unit tests, so I might need some help. Hash cfg test, hash, then inside square brackets we are going like cfg, and then test test. All right, this is done. Inside that we need mod test. All right, what's next? Use super and all these. So you use super, sup. What does that mean? Can somebody explain me? Please explain. What does super mean? Wait. Then you. Oh, so super means all the given above, everything. Use everything. All right. That's what I understood. But let's see what it really means. Now, this test bracket has opened and I don't think it has been closed till here. So yes, we'll go right about that. We'll say test, again a new one. We'll go, yeah, what is happening right now? Ah, it'll never get implemented anyways. So we'll go like this, we'll do this, enter. We'll say test, and hash. Yeah, don't forget the hash and test. Seems right. Inside that we'll have a function test add. Let's get a function test and add, something like this, a small add. Anyways, wait for a moment. Replace with a test add, append what? Let adder be adder, and then result is, let's first do that. Let adder is equals to adder adder, and then let result equals to adder.compute 2.0 3.0. Adder.compute, this is compute that we defined, so it wants 2.0 and 3.0. 2.0 and 3.0, that's what you pass from here. And then we sort of unwrap it, unwrap. I don't think we should do this, but still, since it's telling me, I'm doing it. Then we assert equivalence of result and 5. We assert, equivalence of result, RUSLT, with 5. That's it. That's what we are doing. Oh, not 5, 5.0. All right. Append, oh sorry, 5.0. Is that it? I think so. Now we have to create another test, but let's see. Yes, this seems right. Adder.compute and this unwrap, everything correct. Now we create test. Now test is test divided by 0. So we'll create another test and we'll name it as test divided by 0. Oh shit. Test. Now the name will be here. The test, divide by 0. It seems right about it. Inside that, we will implement something like let divider be divider, divider is equals to div VIDER. All right. Then we must say that let result SULT result equals to what? Divider dot compute 5.0 0.0. Divider dot compute, inside that we'll pass 5.0 and 0.0, which is 0. All right, we do this, we escape, we have to unwrap. All right, so insert, we say unwrap, unwrap w rap. I should be using question mark, but let's go with this. Oh, we are not unwrapping. Good, because we know we are going to get error. Good for us. Otherwise, this would just create some ruckus. We are asserting the equivalence again. EQ, where is EQ? And oh, it's a macro, no? Yeah. So for macros, we have to use this. I've not used it above, so I'll just go right about there and I'll insert. I was already in insert mode, so yes. Now what? I'll say result, isn't it? No, I say matches and then result error. Result should match the error of this. So I say MATCHES matches what? Uh, Matches is also this macro matches assert not equivalence. So we are just asserting. All right, we are asserting. Then matches is result, which is SULT, and then we want ERR of type compute by 0. Compute error, division by 0. Yeah. compute ERR, which is DIVISION by 0. This seems about right. Division by 0. Everything seems nice, clear. Error. The spelling over here. I'll just replace it with capital E. What are we doing over here? Result is result unknown and compute error. And divider is of type divider. We can write it down. We don't write it down. So, all right. It's not that important. Let's go. Create another test, which is for, I guess, multiplication or subtraction, TEST, or a really nice division. So, what's the name of another test? This is done. So, we'll move on. We go to test static execution for multiplier. We go test dynamic execution for subtractor. All right. Run static, run, or so test static execution. Test stat, not static, static execution. 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 Test static execution. Let multiplier is equals to multiplier. All right, that's it. What we are doing is we are dereferencing the multiplier over here. I guess that's what we call it. No, dereferencing the structure, destructuring it. Yeah, we are destructuring the multiplier over here. And then let the result, no, what is this? Result is equals to static exec, and then result, and that is S A T I C E X E C. Static exec, not this, run static. All right, we say run static. Run, run static. Inside that we pass A and B. All right, isn't it? That's what we do now. Yeah, we pass compute, which is ampersand T, and then A and B. Let's see. We pass the multiplier, which is ampersand, mul multiplier without I. So multiplier with I. Then we'll pass A. That is, what is A? 4.0. 4.0. Then we'll pass 5.0. I am not liking these, static numbers, but since it is a test, yes, we need static numbers. What it will give us is something we need to unwrap. So we need to unwrap it. Right? Now we assert equivalence. EQ, which is a macro, it says that RESULT should be 20.0, doesn't it? Yeah, it says that, and then this is done. Now we create another interesting test, which is for dynamic. First of all, create the TEST. Now writing Rust seems so, interesting because it looks nice, it has a feel to it. Now we know what we are doing, and I am loving this experience right now. But I hate an absolute experience where I just stumble into some various, multi-line errors. I hate that. Everybody hates that. That's what I think. Dynamic test for dyna not dynamic, dynamic, YNAMIC EXECUTION execution, which will be of type this. Inside that, we'll have a this time subtractor because we haven't tested subtractor, and we also haven't tested, who, TRACTOR. We haven't also tested this dynamic execution, so we'll do that. Sub TRACTOR subtractor, and that's it. We'll get a result from what? RESULT result is equals to dynamic EXEC, which will have a function called run, not function, I guess it's some method or a function in the module. All right, dynamic. Inside that, we send the subtractor, which is a dynamic type compute. So we'll say subtractor, and then we'll send some values like, what are we sending? 10 and 3. Then we'll unwrap it. We'll send 10 and 3. Then we will unwrap it. I want to see this. So unwrap takes the self, returns F64. So returns the contained OK value, consuming the self value. All right. Because this function may panic, its use is generally discouraged, and panics are meant for unrecoverable errors. and may abort the entire program. Instead, prefer the question mark, the try operator, or pattern matching to handle the error case explicitly. Pattern matching like using match, or call the unwrap or else, or unwrap or default. Panics, so panics if the value is an error with panic message provided by the error's value. Example looks something like this. You have x which has a type of result u32 and ampersand string, and it has a value of OK of 2. Then if we unwrap the x, then we can assert the equivalence between x unwrap and 2, because this takes the self value and eats it and then returns you a value which is after OK, which is 2. So nice one, absolutely bonkers. Now we'll assert assert that a Boolean expression, not this, we want assert EQ. All right, so asserts that two expressions are equal to each other using partial EQ. Assertions are always checked in both debug and release build and cannot be disabled. So see the debug assert equivalence for assertions that are disabled in the release builds by default. So assert EQ is a macro, so we'll use that. Then we'll say result. Inside that, we'll have a result of 10 minus 3, that is 7, isn't it? Yeah. But here it is not 7, it is 7.0. So nice one. I think we have created a ultimate test which will outperform anything we might have thought. It looks nice. Everything feels nice. We are going smoothly. Now the binary example in the bin and main.rs, we have to create this. And after that, we can just test and run, and we are good to go. Since we are not copy pasting the whole code, we have a time to understand and digest what's going on. We'll go in binary main.rs. We'll say that you are, first of all, insert, and we'll say you are from source into binary into what? Into what? Main.rs. All right. That's what you explained him. We use corrected compute engine. Use corrected compute engine. Operation, which is adder, divider. Is that it? Oh, there are multiple operations, but we are only using adder and divider. Then for dynamic execution, we are just running the run dynamic. And for static execution, we are just running the run static. We are adding the main. First of all, let's use this. So use corrected compute engine. use corrected compute engine, and in that we have not adders but operations, and inside that we have adders. So let's get into one line. So we'll write something like operations small o operations. All right, small o operations. Inside them we have multiple things, but we only require adder. We only need adder because we are only going to use the adder, and divider, divider. We can use the multiply and subtractor also, but we for now in this main don't require that. Now after comma we'll say dynamic exec and dynamic exec exec. Inside that we'll need a run dynamic. That's the single program or single function written in that module. Then for static exec exec, we'll be requiring the run static static. That's it. That's what we really want. Comma at the end, but not required anything like that. and this. Now what? This looks bonkers, right? Now we have a main function. All right, let's create a main. Inside that, what? Oh, main function also has a return type right now, which is result of either this, which is unit type, and then inside that we have a box, which I guess stores the pointers. So box dynamic standard error, then error, then we are closing the result. Oh shit! I am seeing two angular brackets. Why? Why is that? Why is that the case? Let's just use it. All right. Then we have for the first time we are creating something like this, where the main also has a return type, which is for now result, which gives us either the unit type, which is empty tuple, or gives us the standard error and error. All right. Then there are two. I don't know why two, but let's go two. And then we are creating a main function. Result TE is a result is a type that represents either success, which is okay, or failure, which is error. So it has a predefined type. We don't need to define it, like I was starting to do it earlier. So let adder is adder, divider divider. Let's do that. And the first, let adder is equals to adder and semicolon. Then let divider be equal to divider. What we are doing, we are destructuring the structures that we have defined. I think so. That's what we are doing. Then we have a result one and result two. So let result one is run static, result two is run dynamic. Result one is adder, result two is divider. Print static add, print static. Will it print the result? Because shit, shit. Duh. And why is this okay? Okay, so we are returning, okay for the main function. All right, all right. So let result without s. So result with s is equals to run static static. Inside that we are passing first of all ampersand adder. Then we are passing what 5.0. We are passing 9.0 as b. Then we'll do unwrap, isn't it? We'll not do unwrap. Unwrap works only for the test. We'll gracefully handle. We'll try if there is any error. Semicolon. That's it. Now we'll print. So print ln, again a macro. So print ln. What we'll print is static static add. Then we'll say result one. Oh, result one. So not just result, it is result one. All right. So result one is run static and ampersand adder, same thing in 5.0, 9.0, and then try. All right, which is question mark. Then we are printing it. Seems about nice. Now again semicolon at the end. So end, use semicolon. Now get a result two. Result two for run, not turn, but run dynamic. I think we have learned a lot today because everything seemed to click in to place after doing quite a lot of labor, intense labor, after being frustrated, after being told some wrong things by ChatGPT. Even after all those tries and errors, we escaped unscathed. Now we are happy and we now know how to write a basic Rust program. This is a macro, so use exclamation. I always forget that, but most of the time forgets it. Dynamic subtract division, DIVID, dynamic divide, which will look something like this. And oh, sorry, we'll say the result to has been received. Divide looks like this, but add is unforgotten. So we have not implemented their display. So will it display? It should, because that's oh shit. We're getting 3 errors right now. Damn you. Ah, why? Because. Very interesting thing. This main has a type which is result. So we have to say it's okay. It's okay. It's okay to return this uh, empty tuple, which is nothing. So now there is no error for third line, but now I see two red marks. Why are they even there? Ah, why are they there? Divider. Did I use divider? I used divider. Adder was adder. So where is the RESULT? RUSELT. I used result run dynamic F64 is equals to everything that was needed. Let's see. Let's escape. Let's come back again. Do we see any errors? Ah, we do see some errors. Why is there some error to it? Why is there an error? I guess because of this, but let's see. Now there's an error over here. Expected a dynamic compute plus static, but found divider. Rust analyzer is going bonkers right now. Dynamic compute. Oh, so I think I made some mistake in run dynamic. So let's check it out. Vim uh, dynamic. Let's see. No, I don't see any errors. We see a dynamic and compute, and I don't see any errors right here. So why is this causing some error? Please don't show any errors. Please don't show any errors. It didn't show any errors. Thank God. So let's go. CLEAR. We clear this terminal. We start to run. Validation checklist is cargo test. First of all, cargo and test. Here we go. Oh, damn. Unwrap, we used unwrap. Oh my God. Public trade compute in compute.rs. Damn it. In lib.rs 20 line. So we'll go to lib.rs, and everything was going so smoothly that I questioned my existence. Unwarp, not unwarp, replace it with replace it with a unwrap. I think it's good to go. And what's next? src compute.rs. So we'll go vim uh, compute.rs in fifth line. What is this? Public trade compute. Is there any error? I don't think so. But let's see. I don't see any errors. So what are you talking about? Compute defines on compute. Perhaps you need to implement it. I just did. So don't teach me that. All right. Oh, it is teaching me that. So let's see. Shit. Assert is wrong. Damn it. Divider is wrong. Shit. So operation.rs. Let's go to operation.rs. If you go that, we'll go to lib.rs. So what we do is we open up a parallel cd into what a project learn into the rust into 06 day 06 not 06 the day inside corrected corrected inside src. Now we clear everything. We see some files, we see an operation. So we go to operation.rs. What is there? I see some methods not found in operation divider because there is a error. Yeah, there was an error. Let's remove it. Now it's a divider. Let's write it. Is there any other lib.rs? Lib.rs. Ah, there is. So assert, which is 42. Line number 42. Where is it? Is this lib.rs? No, this was operation.rs. So we need lib.rs and go to prime equal to, and I see that there is only one s. So now there's assert. Write it. Is there see how many problems are there? Assert, and over here it's assert, everywhere it's assert. Is there any divide? Mhm. Seems about right. Multiplier, divider, adder. Seems about right. Let's close this. What's next? Compute.rs. I don't understand this right now. So this is only a note, I guess. It's not an error. Let's see 5. Now there are one previous error. That is this. Create error. Oh, it's capital error. Oh, I get this. So let's go to, now see, I can understand the error just by seeing it. This is called experience. If this were a little bit more complex, I would have just ran towards ChatGPT to solve all the problems. So let's go, cargo test. Damn, we still have one more. So in main.rs, we should have a dynamic type that is standard.error. But we don't see it over here. Over here, it's just, oh sorry, we see it over there. So yeah, we have to go in bin main.rs. Inside this, now this is a type of result, which is again dynamic, which is box dynamic. All right. So therefore, there was two VOX. There were two V's, and use dynamic. All right. Everything seems nice. Everything is nice. We quit. So we'll come here. We can do test. Shit. How many two errors are there now? The trait standard error is not implemented for compute error. So MPUTE ERROR. This has a type result compute error. Yeah, so does it not exist? The trait standard error is not implemented for question mark operator explicitly performs a conversion on error using value using the from trait. implement from computer. It says something like this. All right. So we'll use P, UMP from here. We'll repeat out everything. Now ChatGPT. What's happening right now? Everything is hanged. Duplicate main.rs? I don't think so. Let's see. Yeah. Yeah. Let's see what is there in main.rs. Oh shit. So remove this main.rs. But this was not even creating some errors, was it? No, there still remains two errors. So this is wrong for library create since you created lib. Should not have these exams errors. So I removed it. What's next? Keep only this. Now typo in lib.rs header comment. File is lib.rs. I don't care about these. Issue is operate operat. You wrote file is operations. Oh, let's keep it clear. Right. Over here, go something like let's go pim operations. Let's go to the top. Let's add operations. Right. Uh, vim vim.rs. These are not even errors here. These are some comments that we don't care about. Just written there for flexibility. Potential error is uses your binary uses but in lib.rs you exported or re-exported the pub use of operation. So you actually do not need operations and divider. Cleaner version would be just adder and divider. All right, let's make that happen. Adder and divider in main.rs. So vim bin and main.rs. Let's go there, and it says that we don't need these adder and then you know divider, just these. Yeah, it got auto refactored. But does that create or solves our test? No, we still have two previous errors, the same two errors remaining. Two errors. So yes, we still haven't solved our issues. Clean final version recommended would be public update librs to re-export execution function and just use these. Final validation is uh, there are so many errors right now, and it's telling me there is no error. See, there are errors like these, and we might need to stop using that question mark and do something else like catch or match or just use and wrap. That is not very safe, but still we might have to use that. Excellent. This is real architecture. Wow, the error is excellent. why this error happens. Your main returns something like this, but run static returns something like result this. So when you use question mark, Rust tries to convert compute error to box dynamic error. That requires compute error to be standard error. So from compute error implementation for box, you have neither. So compiler says compute error does not implement standard error corrected. So how about we just do not return the main function? Whatever the return is, it should get returned automatically. Core rule is compute error does not implement this. So core rule is that question mark operator does error E, then return error from E. So conversion must exist. Proper fix would be prediction correct, will be implement display, and standard error for compute error. Oh shit. I don't want to. I don't want this. But what's the other choice that we have? Implement error trait, compute error. Will error.rs become something like this? Why this fix? Because now compute error implements the error and there exists a blank implementation. So the question mark can convert automatically. Now main compiles. So let's edit our error.rs and then it says that we are good to go. But we have still not even, how many hours? We have been sitting for 5 hours. So and some 30 minutes break. So I don't count that. Vim error.rs and this over here goes back. Over here we have to, this is this enum compute error, and then we have to implement the display for this. So let's go. We'll say oh, we have not imported something. That is very important. So before doing that, implement. We should not use standard fmt, yeah, and then formatter formatter, yeah. Now we can use it. Implement display and for compute error. Oh shit, compute error. Yeah. Now we should implement it by creating a function called what? FMT, yes. For compute error, fmt.display. fmt display function is fmt. Inside that, we have first of all ampersand self, and I guess that's it. Now we have a buffer of f, which is ampersand reference, mutable reference of, which is of type ampersand mutable reference of formatter. I guess so. Yeah. And why did we use this? I don't know. Acha, it's something like this. So we don't care about static t right now. We get a FMT result from this, as we always used to get. What does it gives us? The type returned by formatter method. So FMT and A, B, C. We say this and we get a result. We write and that's it. Yeah. So SULT result. And after that, we start writing using write macro, WRITE. What do we write? We don't write, we match self. So this time we don't write, we match match macro or match, no, match self. Now what? Compute error, overflow, division by error, and invalid error. So for every case we are making right. So if the self is compute with capital ERROR, and if it is overflow, then we are sort of writing WRITE. What are we writing right now? Must be saying something like overflow occurred directly. Oh shit. F, and inside that you're just saying overflow, OCCURED, overflow occurred. Yeah, before comma and after comma. Overflow occurred. Yes. Now we write for compute error, ERROR, for division by 0. Then we say or write something like division by 0, WRITE, and we say F buffer, so get you know DIVI, division by 0. So that's it. Again a comma and compute error, COMPUTE, ERROR, and next is invalid input. Now we use write to just say it is a macro again. So F, and we say invalid input. That's it. And we use a comma again if you want to. If you don't want to, just don't use it. And these are all the returns values, so no need to use semicolon. As for the last statement, it handles the error, standard error for compute error. So yes, yay. So we say use standard ERROR for ERROR for what? Compute error. Oh, ERROR. And we leave it empty so that it gets implemented by itself automatically. We are not using, we are implementing, sorry. My mistake, my mistake. Implementing standard error for compute error. Good for us. Semicolon? No semicolon. All right. Close this. We go over here. We say cargo test. It runs. Oh, it doesn't run. Shit. Error compute doesn't implement standard display again. What the hell is this? What the hell is this? Now it says due to 3 previous errors. So earlier there was only 2 errors. Now there are 3 errors. Public trait error debug. What is this? Where is this? Why is this? Shit. Unsatisfied trait. Error for compute error. Use standard FFT. Did I not just used it? Uh, I did not. This is how it should be, isn't it? Yes. Please don't show any errors. Please don't show any errors. Could not compile due to two errors. So there are two errors still. Invalid. Oh, so a typo is there in line 16. So go to line 16, 16, and there is a typo. Compute in VAL. So this is L, this is I, so invalid input. All right, typo is done. Now only one mistake remains, one error, which is not found this in the scope formatter. Standard FMT is there, and no need to find this formatter. We just use FMT. All right, you go over there and say commutable, back, insert FMT is this, and I guess the error is now gone. Please don't win here. Yeah, everything green, green, green. Okay, okay, okay. Now this is nice. Now what if I want to, run it? How will I? I'll just say cargo run bin main. Cargo run, not bin, run bin, bin. Oh, bin is a flag, so bin, inside that there's a main. Run that. So static is 14, divide is 15. Nice. Deep understanding. Why must we implement the display when implementing errors? Why does question require from E version instead of directly returning the error? Question 3. The main instead return result compute error. Would this error occur? Question 3 is A. B, BECAUSE. Main should never return anything other than void type or std error. That's what I know. Incorrect. Your answer is wrong. Yes, because main should only return false. Rust allows main to return the result. All right. For any type or for any error type E, as long as the E, which is standard FMT debug. Now this is the only requirement. Main does not have a return, box dynamic error. It does not have a return standard error. It can return your custom error type directly. Now the correct answer would be the main returned this, then no conversion is needed. Work directly, no trait error required. So correct answer, no. Why your previous error happened? Because you forced the result box dynamic error. A conversion is required. If you write just this, then no conversion is needed. So that's what we should have written, no? Rust prints the error via debug automatically. Important distinction is this works because compute error is debug. That's enough for me. Now this requires conversion, this error. Because now error type changed, the question mark must convert compute error to box dynamic error. Now answer properly. Why is debug required for main error type to to print it easily using the debug implementation from standard debug or something like that, or something like that. Now I know this is wrong, but I don't even know the right answer, so let's write something. Two. When would returning box dynamic error from main be useful? When we want to get the pointer value of the error with no e moryloccating. What is more explicit for small CLI tools? Result? Well, I guess B. C B. Uh, because then we would be required to implement the box dynamic error for the compute error. Yeah. So I'm back, and this is, yeah, so mostly correct, needs precision. So you said to print easily using debug implementation, the correct direction would be, precise answer is main requires e debug, because if main returns error e, the runtime prints the error using the debug representation. So Rust and E runtime effectively does something like this: e print ln and then whatever the error is. So only debug is required, not display, not error. Now incorrect, because I said we want to get to the pointer value of that error with no heap memory allocating. But this is wrong. The box dynamic error does allocate on the heap. Huh? Now that is the opposite of what you said. Correct answer would be returning this box dynamic error from main is useful when your application may return different error types and you want a single unified error type. Like example, like input output errors, parse errors, custom domain errors. Instead of defining a giant enum, you can erase time into box dynamic errors. Now it is economic for applications, not libraries. So choice is correct choice, but weak reasoning because you chose B, which is correct. Now your reasoning was weak because the correct reason is, for small CLI tools this is sufficient. It is more explicit and simpler because no heap allocation, no dynamic dispatch, no trade object conversion, and clear error boundary. Now, box dynamic error is useful and you truly have a heterogeneous error type. Now we lock this in. Answer precisely. Only one precise reason. Why box dynamic error rarely appropriate libraries? Because we need to implement its display and this would also match the error returned by the functions in main, which which may return different sort of error from implementing this implementing this is inefficient in libraries. Second one precises. Why returning concrete error types better than API stability? Why is returning concrete error types better for API stability? We can manage the error GRACE SQL bar if we know on see the return of the complete error. Let's see. Uh, what does this conversion rely on? Convert compute error into deref into from. Good effort. Now we sharpen the thinking. Incorrect reasoning. You said because we need to implement display and match error in main. Now this is not the core reason. The real reason is box is rarely appropriate in libraries is it erases the concrete error type, reducing the type information and making patterns matching and precise error handling impossible for downstream users. Libraries should expose concrete and well-defined error enums so callers can map the specific variants, handle cases differently. So write exhaustive matches. If a library returns something like box dynamic error, the caller cannot know what errors exist. That weakness API clarity, that weakens the API clarity and stability. Now, question two, partially correct needs precision. So you said we can manage error gracefully if we know concrete errors. More precise would be the concrete error types allows callers to exhaustively match the variant, enabling compile time guarantee when handling the failures. Now, this is about exhaustiveness and API contracts. More precise would be concrete type allows the callers to exhaustively match the variant, enabling the compile time guarantee when handling the failures. Now, this is about exhaustiveness and API correctness, not just graceful handling. Okay. And this is correct because that's what it is. The question mark operator expands roughly to something like match expression at OK V, which is a value, we return value. If E, which is error, then we return error from E. So it relies on from. This is fundamental Rust knowledge. Now we deepen the error architecture. We currently have enum compute error and division by zero invalid input. Imagine this library grows and later add negative inputs. What happens? If downstream user wrote something like error and match error and matched it, but they now get a compile error because there exists something like negative input, and this is not implemented in your errors, which is enum. So this is called breaking change. All right. So Concept is that exhaustiveness and somewhere. So adding a new variant to a public enum is breaking change under the symbol. Unless you mark the enum. Mark the enum how? So pub enum compute error. So non-exhaustive. So if we mark it like it is non-exhaustive, then yeah, this forces downstream users to include a wildcard match also. Now I test you. Why is adding a new variant to public enum considered a breaking change? Because BCAUNC, then the public will not know that there exists error like that. So they might not they shit it's happened. They might not a TCH the wild card possibility with WHICS can protect them from these upcoming errors. All right. Now, what does this non-exhaustive do? It is sort of now it prevents matching. It prevents construction. No, forces downstream. Yeah, match. So this seems right. It forces the downstream wildcard match because now we know that this is non-exhaustive. So any sort of error can occur. So use wildcard. Should internal helper enums be marked? See, I don't know. Have we completed today's tasks? Python is remaining for now, so let's see how much have we completed. Good. First answer evaluation is partially correct. Public will not know error exists and might not match the wildcard. Before, like better explanation would be adding a new variant breaks the downstream code because of the exhaustive match statement will fail to compile. And it is not about not knowing. It is about exhaustiveness guarantees enforced at compile time. So Rust forces the user to handle all variants. Now add a new one, their match becomes non-exhaustive and compile errors. So breaking the change. 2 is correct, which is non-exhaustive, forces the downstream user to include a wildcard arm. You didn't know. Correct answer is internal helper enum. Not read non-exhaustive because they are not part of the public API surface. Only public API types need somewhere stability uh, considerations. Now, have we completed today's task? Let's audit against your Day6 plan. So, static versus dynamic dispatch benchmarking, we did it. You ran multiple experiments, you observed optimization artifacts, you isolated the dispatch cost, you understood LTO inline black box effect, and completed at deep level. Not very deep, but yeah, intermediate. I didn't understood it today, but if I sort of watch these videos back again, I might be able to. So yes. So unit testing discipline. So the tests exist and use of matches were like enum, this enum, and no unwrap in library, only in tests. This is completed. Error propagation architecture. So trade returns result, no unwrap in library, main returns result, and implemented display plus error. Now understood question mark and from. So completed properly. As for the lifetime across module boundaries, we have not done this today. In this corrected version, your original Day6 included lifetime across module boundaries, which is real world context. we have not implemented. As for decision, do you want to finish Day6 completely? Do you want lifetime module properly? Or close Day6 and log it? Move to Python memory experiments. Move to Rust architect topic. Rust architecture topic. If you choose to, I will generate log strict format, your call. So how about we move to now Python, finish Day6 completely. Today's a lot, so let's move to Python first. C. Good. We move to Python, which is system reasoning mode. No ML yet, so pure performance and memory model thinking. So task one is memory bound experiment. We will do this in a controlled steps. Do not run blindly and first understand what you are measuring. So concept one, list, Python list versus, damn it, I've been doing this for, I don't know, 6 days. Python list versus NumPy array. So before writing code, answer, what does a Python list of integer consumes? Why does a far more memory than NumPy array of integers? Because list stores data in text format? No. Because each element is a full Python object? Yes. Uses NumPy, the NumPy uses GPU? No. The list uses heap? No. Answer one. Question one is B. Next, what is stored inside Python list internally? The pointers, and the pointers are pointing towards Python object that are numbers. Pointers which are pointing towards Python object numbers. So yes. Shit. Third question, why is NumPy often memory bandwidth bound rather than CPU bound? Why is NumPy often memory bandwidth rather than CPU bound? Because of memory bound becomes like, fetching everything and calling it becomes slower. Whereas calculating CPU is fast. Since CPU is very fast compared to memory speed and disk input output. Therefore, NumPy is often memory bandwidth bound rather than CPU. Answer first, then we implement the experiment. No skipping. Good. Now we refine your understanding very precisely. So first is correct that each element in a Python list is full of Python object. So for integers, C Python allocates a Python long object, which then stores reference counter, type pointers, and store digit arrays, then heap allocated. So single integer is not 8 byte, it is 28 byte or more, like 36 byte, let's say. And the corrected but expand is correct but expand. So you said the pointer pointing to what? Pointers pointing to Python object numbers. Precise answer would be the Python list stores a contiguous array of pointers. That's what I said, which is Python objects, each pointing to a separately allocated Python object. So memory layout looks like this: a list object, and then there exists the array of Python objects pointers, and they point towards the Py long object, which is the number. two-level indirection. Two level of indirection. A good direction, improved precision. You said CPU is fast compared to memory. More precise would be the NumPy operations are faster, are often memory bandwidth bound because arithmetic arithmetic is vectorized and extremely fast. So performance is limited by how quickly data can be read from RAM and disk, input output. So bottleneck becomes the data movement, not computation. Now we implement the experiment. So there is experiment. Warning is memory usage and all that. Memory is 50 million integer may consume up to these many RAMs and NumPy 400 MB. So I don't want to crash my computer right now because it's already running at 85 and 70%. We'll be using Collab, all right? So it says after running, report exact numbers. Return with these list creation, NumPy creation. That's what it says now. So let's open up the Google Colab and which day is it? Let's go back, not like this. Back, go back, get into Python, uh, activate SOURC, the VNV bin, activate, and after that, CD day 3. Now we make day 4. So ls day ls we say ls the day or day 3 is 3. Yeah. So there's nothing. ls day 2 memory profile.py. Now this is memory test.py. So let me just finish my setting up the environment. Then I'll open this up. Oh, so Hello, hello, hello. So I am back. Well, I took a break also, as well as I was setting up my environment, and now it's totally set up. Now we'll start by writing, the code directly. So we'll write the exact code. So let's start. We'll start by importing some libraries like time. Then we import numpy as np, and we'll import import system. Right? Now we define that n is equals to how many? Oh, 50 million. So n is equals to 50. 50 underscore doesn't matter. It's just used for formatting. Uh, we all know that. I hope so. And see, if we try to print now this n character, what we get is just this 50 million, no underscores. F is the formatter. Inside that, we are saying creating, n elements. EEMPLEEMPS. Hmm. Let's close that. Let's see. All right. So we have created n elements. Now, why is there a backslash? Why? Well, it is not needed because we are not writing C, we are writing Python. But if it says so, we'll just use it. I don't think this will be useful. So it says creating 50 million elements. And if we don't use it, we still get this new line, but not two. We need two. All right. So now we are creating Python list, which is uh, Python list creation, creation. Then we start the counter, start, start the counter, time dot perf, and counter of counter. So it started. We can directly end it, or we can just say list creation, which is we have to minus the start from the ending, so or ending to the start, so that we can get the uh, delta time. So list creation, list creation equals to time dot uh, counter again. Now we are minusing the starting value, start, start. All right. So now we have time intervals. Oh, there's another one. So we'll create a list, which is lst. We will use list, which will be of range, range, capital N. All right, capital N. Now what we try to do is we sort of print, we are IMD, we print the in F format. So format list creation time is this much, which is list creation, creation, and we need only 4 decimal places, not more than that. Otherwise we would get something like 6 or even 8, and it is in seconds. So let's see the output. Yeah, so we are getting the list creation time, which is 1.6202 seconds. Now we do something with NumPy now. NumPy, we'll create array instead of list. Array creation. So we'll start like the same thing. We'll start and then array is equals to np dot arrange n. N is the number like 50 million, and we need it in a type which is called by something called d type, which is data type. So d type is equals to np dot int 64. All right. Now we have a data type in 64, and then we are counting the array creation time. Creation time is equals to time dot per counter, and we are ending it. Now we are minusing it using with the start, which is this. Now we have a time. Now we are printing that time. So we'll say print, print. Inside that, we'll format it. We'll say something like array uh, creation time is this much, which is array creation. And we only need 4 decimal places, up to 4 decimal places. And it is seconds. I think this will also run. Now we are creating list, which is list, then sum. Now what that does is we get a list in sort of sum list, which is a Python method which is written in C Python. So sum, and then we get the sum for the list. And list sum, the the timer ends over here, and we print out. So list sum must take less time than the Python list and more time than the numpys. So yeah, we have done it. So you already know. And then we are doing the numpy sum, which is good. Start is time per counter. COUNTER. And then the ending is something like list and sum. Took some time off, time dot per counter again. Per counter. We say start and we print that list took this much time. And now we say sum. Inside that, we pass the list that we had already over here. Yeah. The list is the list that we have. Now we are benchmarking each. Oh, there was something, some error. What is it? Perf counter array creation. Array creation. What is it? Where is the? Oh shit. NumPy array starts the time dot perf counter, and then arrays np dot arrange type n data type int 64. Array creation took some time, which is dot perf counter, then minus start. Then there shouldn't be any problem, I guess. We are getting a problem, so list creation, this one ran, so we are getting its output. As for the errors. I think this is the place we are getting error from, but why? Don't know. Yes, this was the place we are getting error from. So let's uncomment it one by one. We'll uncomment it, we'll run it. Shouldn't have any sort of error. Then we have array. That is taking np.arrange. Now this line is creating the error. This is np.arrange, which is like attribute module has no attribute. All right. So I think it should not be arrange. It is a sort of a typo over here. It should be array instead of arrange. Why would we need to arrange? We need an array. All right. Now we shouldn't see any errors. Line 17. Yeah, we didn't see any errors. Now it works. So this is a chat GPT's mistake. It's not ours. No, it's ours mistake also because we just typed it blindly. We shouldn't follow anyone blindly, not even ChatGPT itself. Now we have a numpy sum. It runs. Now we'll create a numpy, and then sum. Then we'll start. Oh, we'll start sta start above counter. We get array.sum directly instead of creating it. Array dot sum access shape like this. All right. And what is array? Array is the numpy array. So this is the array. And type of counter should end over here. Counter ends, and we are now subtracting it from the start. start start. Yes, we subtracted, and now we print it. So print print. Say that we use formatter. Format it in a way so that we can see numpy by where are they coming from? I don't see any openings, but there are mosquitoes. Numpy and then sometime. It's numpy sometime is something like array sum and 4.f seconds. Now we shouldn't have any problem till here. Yeah. So now we have to check the memory usage, which is our RAM usage. So we'll get the system library. Yeah, we already have the system library. So we'll just use get size of, which will give us the size of the list, and then nb bytes, which will give us the accurate size for the array, which is numpy's array. So memory usage is that much only. So we are printing now memory usage, usage. We have printf. So we have a format \n memory usage, right? And then we print what? Print something in format Python list or something like lists, and then container container, and then size, and then we mention it, the size it is getting from system dot get size. We have used this library various times, and we have used this get size of multiple times. We have to send our list inside that, and that's it. And we get the size in bytes, so we are mentioning that we are getting size in bytes bytes. All right, I don't think there should be any problem. Now we are printing the same damn thing for numpy array, which is get size of, but instead of using get size of, we are using np.nbytes, which is a precise way to get size for numpy. nbytes, bytes of array. Uh, why is there error? Because it missed its, yeah. Now there shouldn't be any errors. There is a error. So it must have happened somewhere near this. Let's comment this out. Let's try running it again. Yeah, so there is no error except for this. So there is numpy array container. And then we are using array.nbytes. On array, we are using nbytes. Then why are we passing this array? This is not required. Sorry. Then do this. Yeah, there shouldn't be any problem. So we are getting the numpy as a size of 8 bytes, whereas the list contains something like this. What is this? I think there is something wrong. But anyways, let's print it or let's paste it. And that's it. Reduce it to this much. If this is even something near, I don't know, 1000, uh, and it's near if 4G, 1.4, how many bytes? Uh, 1000 bytes, then it becomes the kilobyte. And how many kilobytes? 1000. So 1000 kilobytes make a gigabyte. Is it 400 GB or what? Or is it 40 GB? Shit. Size of. How about we divide it by gigabytes? We do a sort of operation on this. We can divide it over here. How about we divide it from 1000? It will make the bytes into kilobytes, and then again 3 zeros. It will make it gigabyte. Let's run it. We should see some gigabyte. So I'm seeing 400 gigabytes. Is it correct? Let me ask if this is correct. Is this correct? Till then, we've returned everything that it needed. And now question 4. So which operation will be faster? List every time numpy sum, every time, or numpy creation. So what it does is it says use this. Let me shift it for a minute because it's hanging damn too much. It says list. Oh, so it was arrange only. Which notation will be faster? Let's go down, go down, go down. So numpy creation or numpy sum? So numpy creation will be faster, no? D. NumPy sum took, oh damn. Whereas array creation took more time. Shit. Sum took less time than even the creation itself. How about I say, after seeing that data, I say something like NumPy sum should take less time if NumPy is already created, the array. Now, which uses more memory? Estimate approximate ratio. Obviously, list. Fifth. OBIOUSLY. List will take more memory because it nearly STORES 28 to 36 bytes, whereas NumPy only 8 bytes per element. Okay, now let's see this. What's happening over here? We have memory printer, we have this selected arrays printer. Yeah, we took this arrange, corrected, use np.arrange to create an array of n elements. But we did use it and there was then some sort of error to it. But now it works. As for megabytes, we are getting 400 megabytes. And this is, yeah, before gigabyte, megabytes come. Yeah, so this is 4 GB and this is again 4 GB. Mhm. It's hanging too much. It is nearly 100%. My CPU usage is cooked right now. Shit. You reported array creation took this much time, numpy this. This cannot be corrected for 50 million integers. Yes, I know. Therefore, Google improved it. So it says that unit mismatch was there. So system get size list, return size, and when you divide by a million, you're converting bytes into megabytes, not gigabytes. All right. The label gigabyte is misleading. I'll change it to megabyte. And the second thing it did was array.numpy array. Np.array was then creates a scalar array containing a single value, which is this, not an array of n elements, similar to list. This makes the memory comparison between list and numpy array inaccurate. I'll turn numpy array creation and generate array of n elements and adjust its memory display to be in megabytes for consistency. Here's what it did. So now creation time is this much faster. Python list. This is because sometime is this memory usage is this 400 MB, while numpy might seem to use more memory for small number element due to its overhead. For large arrays of elements due to homogeneous type, its contiguous memory allocation can often be more memory efficient than even Python lists, and which stores pointers to individual lists. So this size and get size of list is not very efficient, because the list only contains the pointers. So we are only seeing the size of the pointers in list for Pythons. But what's really happening is, instead of just pointers, pointers are also pointing towards something like a Python object, a pylong, which is now the number, and it has the size of approx 28 bytes. All right. So when you add that 28 byte to this 8 byte calculation, you get a lot of sizes. So that's why. Now, this is the corrected model, correct measurement code. This is the good. These numbers are now realistic. So let's analyze properly. So for 50 million elements, creation list of 1.46 seconds, and NumPy took 0.106 seconds. Sum took approx 0.45 seconds, and NumPy took 0.036 seconds. As for memory, list took approx 400 megabytes. NumPy data buffers, which is 400 megabytes. Now we reason deeply. Why NumPy creation is faster? Python list creation is something looks like this. For each element allocate pylong objects, initialize ref count, and then store pointer, possibly resize list capacity, and repeat 50 million times. Now that is 50 million heap allocations. NumPy creation is something like this: np.arrange, then n, and d type, which is int64. A single contiguous memory allocation, a tight C loop fills the memory. No per element Python objects, no reference counting, no RC, or no refs count, like that. Ref count also exists in Rust, no? It exists. So why NumPy sum is 12 times faster? We know that list sum and all that. NumPy sum, pure C, Python loop in C, and element in Python object must dereference the pointer, loads the pylong, extract the value, add by a Python API. NumPy uses pure C loop, raw contiguous int 64 array, CPU vectorization possible, but no object overhead, no Python interpreter loop, and interpreter overhead dominates list version. Important insight is, you observe that list sum took about 0.45 seconds, whereas NumPy sum took about 0.036 seconds. So NumPy is 12 times faster. Now this difference is not algorithmic. Both are ON, like there is no log, no power, nothing. So it is interpreter overhead plus object indirection versus contiguous memory plus C loop. So important correction is, your memory numbers. This is incomplete because list contains memory which is 400 megabytes only. Now 50 million into 8 bytes gives you this. You did not include the pylon object memory, which is, each pylon is 28 bytes. So the real list memory would look something like this. 8 million, sorry, 50 million multiplied by 8 plus 28, which is 36, which is now 1.8 GB. All right, so where is it? 1.8 GB. The machine is probably using that much. Now NumPy only uses 400 megabytes. So list likely uses 4 to 5 times more total memory, and the concept check is now uh, give me MCQs, and I already know these concepts because CASE, because the give me MCQs. I already know this concept because we are doing this same thing for past 6 days for Python. Don't you understand that? Then we go straight to the tight MCQ evaluation. No explanation unless you fail. So section memory versus CPU versus IO bound. So why do contiguous array benefits from hardware prefetching? They reduce Python overhead. No. CPU can predict next memory address and preload. Yes, this is the answer. So one B. Now next. What is the main reason that Python list iteration is slower than NumPy array iteration? Python list iteration is slower because Python uses linked list. Yes, because Python integers are immutable. What? Python uses recursion. No. Each element access involves pointer different dereference plus object overhead. Yes. So this is the answer. 2 and C. It is not linked list. I'm sorry. It is a list which is now a Python object. I got confused for a bit. If NumPy sum becomes memory bandwidth bound, increasing CPU clock speed will. If NumPy sum becomes memory bandwidth bound, increasing CPU clock speed will nothing, not significantly improve the performance because becomes the memory bandwidth bound. No, so now memory bandwidth is controlling the speed because it can't go much faster than that. So no significant improve in performance. Uh, which scenario is CPU bound? Reading 1 GB file from disk? No. Forming 10 to the power floating point multiplication? Yes. Summing a large NP array? Yes. Allocating Python objects? No. So B and C. So performing 10 to the power 9 floating point multiplications or summing a large NumPy array. So I guess O seems more correct because I know about that. As for performing 10 to the power 9 floating point multiplication, C. B, let's say B or C. C has it out. But let's now go to fifth. So which scenario is memory bandwidth bound? So heavy matrix multiplication, L1 cache? No, this is CPU. Iterating large arrays sequentially? Yes. Opening network socket? Well, it lives on RAM, so but it is not memory bandwidth bound because you are not using that much of CPU, or you are parsing JSON. Yes, but what is bound? So iterating large array sequentially. So this is more memory bound because it doesn't stop. Now, which scenario is IO bound? Input output bound. So calling numpy.sum? No. Sorting 1 million integers in memory? No. Repeatedly reading small files from disk? Yes. Running tight arithmetic loop? No. 6 as value of C. Repeatedly reading small files from disk. Answer in a format 1, 2, 3, 4, 5, 6. Precision only. Well, there is only precision. Uh, it has been 5 hours or more. Damn it. So first is correct. The hardware prefetching relies on predictable memory access pattern. Second is also correct. Correct pointer dereference plus by object overhead dominates. Third is also correct. So if memory bandwidth bound, CPU frequency increases, won't significantly help. Now, for fourth, you said B or C. Incorrect reasoning. This is incorrect reasoning. Correct is B. 10 to the power 9 floating point multiplication is CPU arithmetic bound. Option C, summing large number is typically memory bandwidth bound, not CPU bound. All right. Option 5. No, question 5 has option B, which is correct. Sequential iteration over large arrays is memory bandwidth bound. Now, repeatedly disk reads, which is input output. So score is 5 out of 6. Your only mistake was conceptual confusion between CPU bound and memory bound. That distinction must be sharp. Now, final section, classification tests. So for each scenarios, classify strictly. So CPU bound, memory bound, IO bound. Scenario 1, training a small neural network entirely on RAM on in RAM on large tensors. So in RAM, so it is memory bound, but it also requires, multiplication and all that. So how will I answer? Uh, one, one is memory bound. Copying 5 GB file from SSD to SSD. Now this is input output bound. 2 is input output bound. Power 3. Applying.np square root to 2 GB. Now this is memory bound. Now fourth, parsing these many JSON files, memory bound or IO bound. We are parsing a large file, so it needs SSD and it is using memory, but we need parsing. So we are first of all loading it on RAM and then we are using it. So I think this is memory bound. What is next? Fifth is computing recursively in pure Python. For that, memory bound. Because rather than doing CPU intensive work, we are separating Python objects, pylong and all that. So memory bound. Now incorrect in training small on in RAM on large tensors. You answered memory bound, incorrect. So correct answer, correct classification is CPU bound for compute bound. Why? Because neural network training involves massive matrix multiplication. That's what I thought. But it's on RAM, so yeah, sorry. I got confused. Now copying 5 GB, it is correct. Square root 2 GB, it is correct. Parsing 100 MB JSON file, so it is not memory bound, incorrect. So classification is CPU bound with some input output components. Disk reads happen once and majority of time is spent parsing, tokenizing and constructing Python objects. That's what I said. Now this is CPU plus allocating heavy. All right. This is not memory bandwidth. As for Fibonacci in pure Python, you said memory bound, which is incorrect. It is CPU bound because of heavy function call, interpreter overhead, exponential recursion, no large data movement. Now core rule. Ask what is limiting uh, through throughput. Arithmetic units is CPU bound. RAM transfer speed is memory bound. Disk or network, which is input output bound. Now, quick reinforcement. So answer rapidly. Question 1 is that vectorized A plus B on 5 GB array. Question 2 is, what do I have to do? Answer rapidly. Vectorize A plus B on 5 GB array. Let's do it. CPU, memory or disk. I'll write it like that. Vectorized A plus B CPU. Since it's vectorized, we'll use just CPU. 2. SHA hashing 2 GB buffer already in RAM CPU. Downloading 10 GB file over 100 Mbps connection network and IO. Compiling large Rust projects. Compilation requires CPU. CPU. Answer only classifications. There is no fifth. Everything is required. What is required more, what is required less? Who knows? You answered CPU. Correct is memory bound. Well, good for you. Reason one simple addition per element, arithmetic cost tiny, moving 10 GB data to input plus output dominates, limited by RAM bandwidth. Now, 2. SHA-256 hashing 2 GB buffers already in RAM. Yeah, correct. CPU. 3. Downloading, you said network and IO. We classify bottleneck type as IO bound network IO. Be concise. That's what I said now. Compiling large Rust project. We said CPU. Mostly correct. Compilation is typically CPU bound. Though it may be some IO, primarily bottleneck is code generation and analysis. You left blank, that indicates you rushed. A final reinforcement. There was no question, so final reinforcement question. Sharp thinking. Classify each correctly. So sorting. Let's go. Sorting 2 GB array already in RAM. Now this is CPU intensive because we need calculation. Damn it. One CPU. What is the second one? Reading 2 GB CSV file from HDD. Uh, two is two is IO. Three, because HDD is far slower than a RAM and far slower than a CPU. Now running np.sign function on 10 GB array. So sorting, storing, all that will create some memory. Sign also requires calculation, but it's not that much. That 10 GB array to be loaded on the RAM and then using it is far more than just calculating it. Now rendering 3D scenes with heavy ray tracing. Well, it is mostly on CPU, but we use GPU, which is a processing unit, but for graphics. A fifth one, uh, copying 2 GB memory block using memcopy. So every bit is being copied. So input output, I guess, IO and memory IO 2 GB. Sorting 2 GB array in RAM, correct. This is also correct. NumPy sent incorrectly, mostly because correct classification would be CPU bound. Vectorized compute heavy. But it is also 10 GB, no? So sign is expensive transcendental math, much heavier than simple addition. And arithmetic cost dominates memory. Memory matters, but compute dominates. A rendering 3D scene with heavy ray tracing answered CPU, but CPU correct classification would be CPU or GPU bound, which is compute bound. So ray tracing is massively compute heavy. Acceptable answer is CPU bound or GPU bound. So memcpy, which is 2 GB memory block, you answered IO and memory incorrect. Correct classification would be memory bandwidth bound. which is memcp, why moves data in RAM, no disk, no network. But to move that data, you need where are you moving that data from? You are moving that data from some sort of SSD or hard disk, something like that, file store, whatever. Now, core heuristic. If operation per element is simple, like add, then multi, whatever. You have a day6 log, so I think Python section is again done mostly. So simple is that add, multiply, memory bound, sign, exponential, hash, and crypto, CPU bound, disk and network involved, then input output bound, and Python section is complete. You now understand C Python object overhead and pointer indirection cost, contiguous memory advantage, memory bandwidth limit, and CPU versus memory versus IO bottleneck. All right, so this is now finished. Let's end it. Bye bye.